Hello there, and welcome to Life Beyond Seen, where we take the things that seem distant, cold, ancient, or a little unsettling, and sit with them long enough to understand why they stay in the mind long after the lights are out. Tonight, we are heading north, far north, to a place that most people will never visit, a place that on the map looks simple enough. A white cap at the top of the world, a quiet edge, a frozen border, the sort of place people imagine as empty, flat, and still, as though the planet simply ran out of things to say and covered the silence with ice. But the Arctic has never really been quiet. It only looks quiet from very far away. Beneath that pale surface is an ocean. Not a friendly blue holiday ocean with postcards and striped umbrellas, and someone trying unsuccessfully to assemble a beach chair. This one is colder, darker, heavier, and far less interested in making visitors comfortable. It lives under shifting sheets of sea ice, under months of darkness, under storms, pressure ridges, fractures, fog and temperatures that can turn the simplest task into a slow negotiation with numb fingers and poor life choices. It is one of the hardest places on Earth to study properly, and even now, after satellites and submarines and research vessels, and enough sensors to make a refrigerator look underqualified, the Arctic Ocean still keeps a surprising amount to itself. That is part of the problem. Part of the scientists are not usually frightened by things they understand well. Annoyed by them, yes. Deeply underfunded by the effort required to study them, also yes. But genuine unease tends to begin when a place is active, important, changing, and still only partly visible. The frozen ocean beneath the Arctic checks all four boxes with almost rude enthusiasm. Before we settle in though, let me ask you something simple. Where are you listening from tonight? Is it late where you are? Is the room warm? Is there rain at the window, traffic in the distance, a fan humming in the corner, or are things almost completely still? I like that thought, really. That while we talk about one of the coldest and most isolated parts of the planet, you might be curled up somewhere comfortable, perhaps with a blanket, perhaps with tea, perhaps already regretting the decision to learn about hostile polar waters right before sleep. A fair concern, honestly. This may not be the most obvious bedtime material, although history shows that human beings will absolutely listen to hours of deeply unsettling science, as long as the voice remains calm enough. And if that sounds like your kind of evening, do take a moment to like the video, subscribe to the channel, and settle in with us here at Life Beyond Seen. It helps more than you might think, and it means this strange little tradition can continue, where we wander into difficult subjects gently, without shouting, without dramatic music trying to convince you that every snowflake is part of a conspiracy, and without anyone saying you won't believe what happened next, which is always a phrase that makes me believe significantly less. Now, when most people picture the Arctic, they picture the top. Ice, snow, maybe a polar bear in the middle distance looking like the official spokesperson for clean air and poor planning. Maybe an icebreaker ship inching through a field of shattered white slabs. Maybe a sky with that blue-grey colour that seems to belong only to very cold places. What they usually do not picture is the enormous body of seawater underneath. A whole ocean, moving constantly, carrying heat, salt, nutrients, sediment, carbon, organisms, and old stories from one part of the planet to another. The ice makes it seem sealed. It is not sealed. It is a lid that shifts, cracks, thins, reforms, drifts, and sometimes vanishes where it used to hold. That alone is enough to keep researchers awake. Because the Arctic Ocean is not just scenery. It is not a decorative frozen bowl placed at the top of the globe for cartographic balance. It is part of the machinery of Earth's climate. It helps regulate temperature differences between regions. It interacts with the atmosphere in ways that affect weather far beyond the Arctic itself. It stores and releases heat. It reflects sunlight when ice is present. It absorbs more energy when darker water is exposed. It influences ocean circulation. It receives fresh water from rivers, melting ice, and precipitation. It hosts ecosystems that function under conditions that would make most living things turn around politely and try somewhere else. And right now, many of those systems are changing faster than scientists would prefer. There is something especially troubling about a place that has long been treated as stable, beginning to behave differently. Not because change is unusual in nature. Nature changes constantly. But some forms of change are gradual enough for systems to adjust. Others arrive like a floorboard giving way under a carpet. You thought you understood the room. Then suddenly one section drops half a metre, and everyone becomes much more interested in structural integrity. For a long time, the Arctic was described in language that sounded permanent. Multi-year ice, deep freeze, polar cap, frozen ocean. Words like that give the impression of something fixed and reliable, even if harsh. Yet the scientists who work there know better. Sea ice moves. Ice thickness varies. Wind can drive fractures over long distances. Warmer water can slide into places it used to struggle to reach. The seafloor itself carries the marks of landslides, ancient ice coverage, and methane seep activity. Under the ice, sound travels in strange ways. Light behaves differently. Seasons are extreme. Equipment fails. Batteries lose their nerve. Instruments vanish. Moorings snap. Weather closes in. Helicopters cannot always fly. Ships cannot always advance. In some regions, the maps of the seabed were, until recently, much less complete than one might hope for a place involved in the future of the global climate. That is another thing people often forget. Parts of the Arctic seafloor remained surprisingly undermapped for a very long time. We had in some cases better models of the surface of Mars than of sections of our own ocean floor. There is a certain humility in that. Also a certain embarrassment, though science tends to frame embarrassment as an ongoing opportunity for further research, which is a very graceful way of saying, we really should have looked under there sooner. And when scientists do look under there, the findings are not always comforting. Some of that discomfort comes from scale. The Arctic Ocean is not the biggest ocean, but it is deceptive. Under the ice lies a basin system with ridges, slopes, shelves, deep plains, and gateways connecting it to other oceans. There are continental shelves broad enough to matter enormously for productivity and carbon cycling, and deep central areas where water masses sit layered according to temperature and salinity in ways that are stable until, one worries, they are not. The upper layers can be cold and relatively fresh. Deeper Atlantic origin waters can be warmer and saltier. That arrangement matters. The boundary between them matters. Changes in mixing matter. If warmer water from below or from inflowing currents reaches the underside of sea ice more effectively, the consequences do not remain politely local. Some of the unease comes from timing. The Arctic is warming faster than the global average. That sentence appears so often now that it risks sounding almost ordinary, which is unfortunate because there is nothing ordinary about it. Scientists measure reduced sea ice extent, thinning ice, changing seasonality, altered habitat ranges, coastal erosion, thawing permafrost on land, and wider knock-on effects that stretch into weather patterns, ecosystems, shipping routes, geopolitics, and carbon feedbacks. A frozen region that once acted like a strong reflective shield is, in places and seasons, becoming darker and more absorbent. White ice reflects sunlight well. Open water does not. That difference is not subtle. It changes how much solar energy the ocean takes in. More absorbed heat can mean later freeze up and thinner ice later on, which can mean more open water again. Scientists have a phrase for loops like that. Ordinary people have another phrase. That does not sound ideal. Still, raw climate numbers are only part of what makes the Arctic Ocean unsettling. The deeper fear comes from the combination of importance and uncertainty. This is not a place where one missing detail affects only a footnote in a specialist paper. The Arctic links into systems that affect fisheries, coastlines, storms, and temperatures far from the pole. If there are thresholds, delays, amplifiers or weak points in that frozen ocean system, people want to know where they are before crossing them, preferably well before. Science, as a rule, enjoys identifying the cliff before the vehicle reaches it, and yet the Arctic does not make that easy. Imagine trying to study a dark, moving, freezing ocean from a platform that itself cracks, drifts, and sometimes disappears. Imagine lowering instruments through ice holes while weather conditions remind you that fingers are optional, but paperwork about frostbite is forever. Imagine deploying moorings beneath sea ice and hoping to retrieve them months or years later. Imagine autonomous vehicles operating under ice, where surfacing is not a reliable option because the ceiling is solid. Imagine collecting biological samples in a place where seasonal timing is shifting, so the calendar that used to guide blooms, migrations, and feeding cycles no longer behaves quite the way it once did. That is before we even reach the political, logistical, and financial complications of doing polar research at all. This is why the Arctic can feel, to scientists, like a place where several hard problems have agreed to collaborate. It is remote, but not irrelevant, dangerous but not dramatic in the obvious way. It does not terrify with sudden spectacle as often as with quiet implications. There is no single villain standing in the snow twirling an icicle moustache. There is instead a network of interacting processes: sea ice decline, ocean warming, freshwater changes, ecosystem shifts, possible methane release in some regions, coastal destabilization, more human access, more noise, more extraction interest, more shipping, more risk of accidents in places badly suited to rescue or clean up. The Arctic does not need theatrical monsters. It has systems, and systems are much better at causing trouble over long periods. Consider the sea ice itself. To a casual observer, ice might seem like a static shield, a protective shell sitting above the ocean. In reality, sea ice is dynamic. It forms, thickens, drifts, collides, piles up, fractures, and melts. Multi-year ice, the older, thicker ice that survives summer melt, has been declining. Thinner first-year ice is more vulnerable. Leads, the open cracks in sea ice, can expose ocean water to the atmosphere. Pressure ridges can make travel treacherous. Melt ponds can darken the ice surface in summer and increase heat absorption. A region that appears white and simple from space may, on human scale, be a difficult patchwork of conditions changing over hours or days. Now place an ocean beneath that, one structured in delicate layers. Saltier water tends to sink below fresher water. Cold and heat move according to gradients that do not care whether the researchers on deck have had lunch. In parts of the Arctic, relatively warmer Atlantic water enters below colder surface layers. As long as stratification remains strong, a good portion of that deeper warmth stays separated from the ice above. But if mixing increases, if layering weakens, if currents change, if local conditions allow more heat upward, then the underside of the ice becomes more exposed to warmth from below. The ocean, in other words, can attack the ice from beneath, while the atmosphere works from above. Being squeezed from both directions is rarely a recipe for long-term confidence. Then there is the seafloor, because of course the Arctic also has secrets underneath the water itself. Continental shelves on the Arctic margins contain sediments rich in organic material. Some areas show methane seeps, places where methane escapes from the seabed into the water column. Methane is a powerful greenhouse gas, and the question of how much might be released from Arctic systems under warming conditions has been studied intensely. The situation is complex. Not every methane bubble reaches the atmosphere. Water depth matters, oxidation matters, transport matters. Scientists are careful here, and careful for good reason, because this is one of those topics where public conversation can leap straight from interesting research question to planetary doom by Tuesday. Real science is slower and usually less theatrical than that, but the basic point remains. The Arctic holds carbon in vulnerable forms across land and sea systems, and understanding how stable those stores remain is not optional. Even the soundscape under the ice adds to the strangeness. We tend to think of frozen places as silent. They are not. Sea ice grinds, cracks and groans. Whales call through dark water. Ships introduce noise where routes open. Storm energy can travel through water and under ice in ways that reshape what animals hear and how researchers listen. Acoustic monitoring in the Arctic has revealed environments that are alive with signals, some biological, some mechanical, some geological, some still being interpreted. It is unsettling in a very specific way to realise that a place assumed to be blank is, in fact, busy. Busy places are harder to predict. And then there are the living things. The Arctic Ocean supports food webs that depend on precise timing and harsh conditions. Tiny algae grow in and under the ice. Zooplankton feed on blooms that arrive with seasonal light. Fish, seabirds, seals, whales and polar bears all connect, directly or indirectly, to those cycles. When ice arrives later, leaves earlier, or becomes less reliable, those timing relationships can shift. Some species adapt, some move, some struggle. New species may expand northward. Parasites and diseases can change range. Fisheries questions become more complicated. Nothing in ecology exists alone for very long. Change one repeating condition, and many other patterns start reconsidering their commitments. The image many people have of fear in science is dramatic. A red alarm, a siren, someone in a lab saying, "This should not be happening." In the Arctic, fear often looks different. It looks like a series of papers that become less reassuring over time. It looks like phrases such as faster than expected, previously rare, increasing variability, and poorly constrained. It looks like models that need revising because reality is not stuck to the old script. It looks like veteran researchers saying that features they once counted on as normal now arrive earlier, later, weaker, thinner, or not at all. It looks like the slow realization that a region once buffered by cold is becoming more exposed to all the messy habits of the modern world. Because exposure changes everything. As sea ice retreats seasonally, human activity can expand. Shipping routes that were once more theoretical become more viable in certain periods. Tourism increases, resource interests intensify, military attention follows, fishing pressures may change, and every added vessel, every engine, every spill risk, every navigation error, every piece of noise, every policy disagreement arrives in a place with limited infrastructure and ecosystems already under strain. Operating in the Arctic has always been difficult. Operating there more often does not automatically make it wise. What makes scientists especially uneasy is that the Arctic rarely offers isolated effects. Things stack. Warmer air can reduce ice. Less ice can increase ocean heat absorption. More open water can alter wave action and accelerate coastal erosion. Freshwater inputs can affect stratification. Ocean changes can affect ecosystems. Human access can increase disturbance. Disturbance can complicate monitoring. Monitoring gaps can delay understanding. Delayed understanding can delay response. It is one of those regions where every answer seems to arrive holding hands with 3 more questions. And yet, for all of that, the Arctic is not terrifying because it is empty. It is terrifying because it is active. Beneath the frozen surface is a system constantly doing things. Circulating, reacting, storing, releasing, feeding, cracking, warming, refreezing. Remembering old conditions in sediments and ice, then quietly moving into new ones. Scientists do not fear blank spaces as much as changing systems they cannot fully observe in real time. The Arctic Ocean is exactly that sort of place. So when people say the frozen ocean beneath the Arctic still terrifies scientists, they do not mean researchers are standing on the deck of an icebreaker, whispering ghost stories about sentient glaciers. Though after several weeks in the cold, I suspect even a mildly aggressive snowdrift can begin to look personal. They mean something more grounded than that, and in many ways more serious. They mean the Arctic combines importance, vulnerability, speed of change, and incomplete knowledge in one difficult region. It matters globally, It is hard to monitor, it is changing quickly, and some of the processes unfolding there may carry consequences well beyond the polar circle. That is enough to make any careful scientist uneasy. Because once you move past the postcard version of the Arctic, once you stop seeing it as a white patch and start seeing it as a living ocean under pressure, a different picture comes into focus. Not a dead zone, not a still wasteland, not an empty freezer at the top of the map. Something far stranger than that, and far more alive. The surface may look frozen, but underneath, nothing is really sleeping. That is the first trick the Arctic plays on the mind. It persuades people, from a distance, that a frozen ocean must be an inactive one. The surface looks blank, white, flat, quiet, and in photographs often almost too clean, as though nature had tidied the whole region just before the camera arrived. No visible waves, no palm trees trying to hold on in a crosswind, no bright reef fish making questionable life choices near tourists with waterproof cameras. Just ice, sky, and the general impression that if anything is happening at all, it is probably happening very slowly and with a great deal of frost. But that impression falls apart the moment you look more carefully. An ocean does not stop being an ocean because someone put a lid on it. It does not pause out of politeness. Water still moves, heat still moves, salt still moves. Organisms still feed, hunt, drift, and reproduce. Currents continue threading through the basin. Layers remain stacked in uneasy order. Tiny changes in temperature still matter. Pressure still presses. Cracks still open. Ice still shifts. Even in the months when darkness settles in for long stretches and the surface appears locked, the system underneath goes on working without any concern for whether human observers find that convenient. That is one reason scientists speak about the Arctic with such caution. The place looks still at the exact moment it is doing a great deal. There is something uncomfortable about hidden activity. Human beings like motion when it is visible and preferably labelled. We are much happier with a train if we can see the tracks and read the timetable. An invisible machine under a floor is a different matter. We begin to imagine belts, gears, loose bolts, and an ominous warranty situation. The Arctic Ocean produces a similar kind of unease, not because it is supernatural, but because it is full of ordinary physical processes happening in a place that hides them well. Take sea ice, for example. A person seeing it for the first time might assume it behaves like frozen pavement, hard, fixed and dependable, if terribly inconvenient for bicycles. But sea ice is not a parking lot. It is a moving, deforming, seasonal cover made from frozen seawater, and it behaves more like a constantly rearranging platform than a solid floor. Winds push it, currents pull it, flows collide and pile up, leads open, sometimes suddenly, revealing strips of dark water between fields of ice. Pressure ridges rise where slabs are forced together, creating jagged formations that can be far thicker below the surface than above it. What looks like a smooth white sheet from overhead can, at close range, turn out to be a rough, fractured landscape with hidden weak points and shifting edges, and all of that motion above reflects and influences motion below. Under the ice, the ocean is layered in ways that matter immensely. Surface waters in the Arctic are often relatively cold and in many places fresher than the deeper waters beneath them because of river input, sea ice melt and other freshwater sources. Beneath those upper layers are saltier waters, and in some regions warmer Atlantic origin waters enter at depth. Temperature and salinity together control density, and density controls a great deal about where water settles and how easily different layers mix. This is not the sort of topic that usually dominates small talk at dinner parties, which is a shame because once you understand it, half the Arctic starts making more sense. The short version is that the ocean can keep different water masses separated for long periods if density differences are strong enough. That separation matters because some of the deeper water is warm enough, relative to the freezing point of the water above, to melt ice if it reaches the underside efficiently. So the stability of the layering is not a minor technical issue. It is central to how the frozen surface survives. Scientists spend a great deal of time trying to understand how much warmth is trapped at depth, how that warmth moves, and under what conditions it can mix upward. Because once you have warmer water lurking below colder surface layers, the whole system starts to resemble a very bad surprise waiting under a thin mattress. It may remain contained for some time, but nobody with a practical mindset is going to ignore it. Even when the water masses remain layered, the ocean is not idle. Currents circulate through narrow gateways linking the Arctic with the Atlantic and Pacific. Water enters, transforms, cools, freshens, sinks, rises elsewhere, exits again, and participates in a global circulation system that connects the far north to much lower latitudes. The Arctic does not sit apart from the rest of the planet like a forgotten freezer drawer filled with old peas and one deeply confusing bag of ice from 2019. It is connected. Water entering from one region carries heat and salt signatures from somewhere else. Water leaving the Arctic can affect downstream conditions beyond the polar basin. That is why changes there do not stay there. Then there is the matter of time. In temperate oceans, surface waters warm and cool through the year, in patterns people can imagine easily enough. In the Arctic, seasonality is more extreme and, in some respects, more deceptive. There are long periods of darkness and long periods of light. There are phases when the surface looks nearly lifeless, and then there are bursts of biological activity when light returns and microscopic producers take advantage of the opportunity with astonishing speed. Much of Arctic life is adapted to this pulse-like rhythm. It waits, endures, and then moves quickly when conditions allow. At the base of the food web, tiny algae grow within and beneath sea ice, and in open water when light and nutrients line up. These are not glamorous organisms by conventional standards. Nobody makes blockbuster films about algae finding purpose beneath a pressure ridge. Yet they are essential. Their growth supports zooplankton, which support fish, which support birds, seals, whales, and on upward through the food web. A system can look empty to human eyes and still be full of biological urgency at scales we are not naturally built to notice. That mismatch between appearance and reality is everywhere in the Arctic Ocean. A person looking out over a frozen expanse might think, nothing much is happening. A scientist looking at the same scene may think about ice algae, under-ice amphipods, copepods managing their life cycles, cod moving through cold water, seals using breathing holes, belugas navigating acoustic space, and microbial communities carrying on with impressive dedication in conditions that would make most office workers send a firmly worded email. The ocean is not sleeping. It is simply not advertising. There is also the question of darkness. Darkness, for humans, has a talent for making active places seem more inactive than they are. When we cannot see motion, we underestimate it. But under Arctic ice, darkness is normal for long parts of the year, and life does not stop because the sun is absent. Some animals rely on senses other than vision. Some track faint light changes better than we can imagine. Some feed in narrow windows. Some conserve energy. Some move under the ice canopy in search of food or shelter. Fish do not gather for a committee meeting and agree to suspend all operations until conditions become more scenic. Whales in particular make the point rather well. Species such as bowheads, narwhals and belugas move through Arctic waters using acoustic awareness in ways humans can admire but not really match. Under ice, sound behaves differently than it does in open air, and the Arctic is often better understood through listening than through looking. Scientists deploy underwater microphones to record calls, ice noise, ship traffic, and other sounds that reveal patterns hidden from sight. The results do not suggest a dead ocean. They suggest a place full of communication, navigation, fracture events, movement, and interference. That last part matters increasingly. As the Arctic becomes more seasonally accessible in some regions, human noise enters environments that evolved under very different acoustic conditions. Ships produce low-frequency noise that can travel far underwater. Industrial activity adds more. Marine mammals that depend on hearing may find navigation, feeding, or communication disrupted. It turns out that when people say an ocean never sleeps, they also mean it notices when someone noisy arrives uninvited. The Arctic has had little reason to appreciate marine traffic as a lifestyle enhancement. Beneath the ice, even the chemistry is busy. Gases exchange where water meets atmosphere through leads and open water. Nutrients move through layers. Organic matter sinks. Microbes break it down. Carbon cycles through living and non-living components of the system. Some regions absorb carbon dioxide efficiently. Others reflect local complexity that makes broad generalizations risky. Scientists studying ocean chemistry in the Arctic are not dealing with a simple tank of cold water. They are dealing with a responsive system where physical, chemical and biological processes interact continually, and where change in one part can push against the rest. One of the most important of those interactions involves ice itself as habitat. Sea ice is not just a cap lying on top of the ocean. It is an environment. It has brine channels, rough undersides, trapped pockets, attached algae, visiting invertebrates, and seasonal roles in the lives of larger animals. Lose ice, and you do not merely lose frozen water. You change light conditions, habitat structure, nutrient timing, foraging routes, predator-prey interactions, and the physical relationship between air and sea. That is part of why less ice is such a loaded phrase. It sounds simple and is not. The trouble is that people often think of change in terms of disappearance alone. Ice melts, water opens, done. But Arctic change is more complicated than subtraction. Sometimes it is rearrangement, sometimes it is substitution. Sometimes thinner seasonal ice replaces thicker multi-year ice. Sometimes species shift ranges. Sometimes bloom timing changes. Sometimes storm exposure increases because open water allows waves to build. Sometimes warmer inflows arrive in ways that alter mixing and ecosystem structure. The ocean keeps functioning, but not in the same way, and not with the same confidence that older patterns will continue. That is why scientists are uneasy when they talk about an Arctic that looks lifeless. It is not lifeless, and that false impression can delay understanding. If the public imagines the region as empty, then the stakes sound low. Empty places feel easier to sacrifice. Empty places sound less urgent. Yet the Arctic Ocean is full of relationships. Many of them delicate, many of them tied to conditions that are changing right now. Some of those relationships happen on the seafloor, which is another part of the system most people never picture when they imagine the Arctic. Under the water column, beyond the ice, beyond the drifting animals and suspended particles, the seabed hosts its own communities. Worms, clams, crustaceans, microbes, and a long list of creatures with names that rarely make evening conversation all participate in a benthic world, shaped by food supply, sediment type, currents, and water properties. On broad continental shelves, organic matter raining down from surface productivity can support rich bottom communities. In deeper basins, life may be sparser, but it is not absent. The Arctic seafloor is not decorative, it is occupied. And in some places it is geologically interesting in ways that keep researchers paying close attention. Methane can seep from sediments. Old glacial histories are recorded in seabed forms. Submarine landslides have left scars. Sediments preserve clues about past climates and former ice coverage. Every core sample pulled from the Arctic floor is, in a sense, a report from a place that has been keeping records longer than any weather station. The challenge naturally is that the records are not filed under user-friendly headings like things you were hoping would remain stable. There is also a basic psychological reason the frozen ocean feels more alarming once you understand it better. It is one thing to worry about a storm you can see. It is another to worry about a large system that can alter itself from below, from within, or from interactions too slow for casual attention. The Arctic teaches that lesson repeatedly. Ice can thin from the bottom. Warm water can move into unexpected places. Biological timing can shift without a dramatic headline. Carbon processes can matter long before they become visible to anyone outside specialist circles. It is the kind of environment where subtle changes may be more consequential than spectacular ones. Science is built in part to notice subtle changes before they become disasters. That is why Arctic monitoring matters so much, and why it is so frustratingly difficult. Instruments placed under sea ice may record temperature, salinity, currents, oxygen, or sound for months at a time. Moorings anchored to the seafloor collect data while the surface drifts overhead. Satellites watch the ice from above but cannot easily tell the whole story of what lies beneath. Autonomous underwater vehicles can map and sample, but operating under ice is a serious technical challenge. Research cruises face weather, ice conditions, cost, and limited windows of access. Scientists are, in effect, trying to understand a restless machine while working through a narrow access panel in freezing wind. And still, piece by piece, the picture has become clearer. The Arctic Ocean is dynamic in every sense that matters. It is physically active, biologically active, chemically active, and increasingly active as a site of human interest. The old assumption that it is basically a frozen blank at the top of the world never really survived contact with good data. It only survived because the place was hard to reach and easy to simplify. Even the phrase frozen ocean can be misleading. It suggests totality. In reality, some areas remain open, some freeze seasonally, some carry thinner ice than before, some retain older ice longer than others, and local conditions vary enormously. There is no single Arctic condition that applies neatly everywhere. One shelf sea does not behave exactly like another. One year does not resemble the next in all respects. Regional detail matters. Scientists know this, which is why they sometimes sound frustratingly cautious when asked broad questions. They are not being evasive. They are trying not to flatten a complex system into a slogan. Still, some broad truths remain useful. One is that the Arctic stores memory. Not memory in a mystical sense. Memory in the practical, physical sense. Ice thickness carries the history of growth and melt. Water properties reflect where that water came from and what happened to it. Sediments record past conditions. Ecosystems reflect repeated seasonal patterns until those patterns shift. Another useful truth is that the Arctic also responds quickly once certain conditions change. Thin ice is more vulnerable. Open water absorbs more heat. Small shifts in timing can affect feeding success for species living on narrow seasonal margins. A place can be both slow to reveal itself and fast to react. That combination keeps people on edge. For all its reputation as a remote wilderness, the Arctic Ocean is not beyond influence. It receives signals from the rest of the planet and it sends signals back. Greenhouse warming does not stop at the polar circle. Ocean heat transport does not end because a map becomes whiter near the top. Pollutants can reach the Arctic through air and water pathways. Plastic has been found in Arctic environments. Industrial interest is expanding. Fishing pressure and shipping routes are subjects of growing attention. Even where direct disturbance remains limited, the assumption of isolation is no longer reliable. The frozen ocean beneath the Arctic is part of the modern world now in a way that makes many scientists deeply uncomfortable, because modern attention tends to bring extraction, noise, traffic, and deadlines, none of which are especially known for improving fragile systems. And perhaps that is the strangest part. A place that looks empty can be overloaded. A place that looks silent can be full of signals. A place that looks inert can be changing quickly. The Arctic teaches that appearances are often worst exactly where understanding needs to be strongest. So when researchers talk about this ocean as though it never sleeps, they are not being dramatic for effect. They mean that under the surface there is always movement, always exchange, always life, always pressure, always some process carrying consequences into the next hour, the next season, the next year. The ice cover may hide the water, but it does not calm it into stillness. If anything, the concealment makes the activity more unsettling, because it asks scientists to trust instruments, models, fragments of observation, and long experience in a place that is never fully visible at once. That is why the first serious look beneath the ice changed everything. Once expeditions began measuring more carefully, listening more carefully, sampling more carefully, and mapping what had long been poorly known, the Arctic stopped looking like a frozen pause at the top of the world and started looking like what it really is, an active ocean system with too much at stake to misunderstand. And the more closely scientists looked, the more they realised that the most worrying part was not simply the cold, or the darkness, or even the ice. It was what the instruments were starting to show beneath it. And when scientists finally began looking beneath the Arctic ice with better tools, longer records, and a little more humility than the region usually allows, what they found was not a silent vault of frozen water. They found motion. They found heat where many people assumed there should mainly be cold. They found life in places that looked far too dim and harsh to support much of anything. They found a seafloor that had been mapped far less completely than most people would guess. They found an underwater world that was not only active, but in some ways far more complicated than the surface had ever suggested. One of the first unsettling discoveries was that the Arctic Ocean is stacked like a very nervous layer cake. Near the surface, the water is often colder and fresher, shaped by melting ice, river runoff, and the general habit of the Arctic to dilute things just enough to make oceanographers squint at their instruments and ask for one more deployment. Beneath that upper layer, however, scientists found warmer, saltier Atlantic water entering the Arctic and slipping underneath the fresher surface water rather than mixing straight upward. That layering is important because it means the ocean can hide warmth below a relatively cold lid. In some places, that hidden warmth has remained partly separated from the ice above by the density structure of the water. In other places, researchers now worry that the separation is weakening, and that is when the Arctic starts sounding less like a freezer and more like a system storing trouble below the shelf where the guests cannot see it. This deeper Atlantic influence is not just a technical detail that lives in graphs and politely alarms specialists. It changes how the whole ocean behaves. NOAA's 2025 Arctic Report Card notes that Atlantification, which is the spread of water properties from lower latitudes into the Arctic, has reached the central Arctic Ocean, hundreds of miles beyond where the former edge of Atlantic influence used to be described. The same report warns that this process can weaken the layering of waters with different densities, increase heat transfer, melt sea ice, and threaten circulation patterns that help shape weather over the long term. That is not the kind of finding that makes scientists relax and go home early. It is the kind of finding that makes them bring more sensors next year and then realise the sensors need their own sensors. Another major discovery was that the underside of sea ice is not barren. For a long time, many people assumed thick ice blocked so much light that there would be only limited biological activity beneath it. Then researchers began finding under-ice blooms, including large blooms of phytoplankton under Arctic sea ice, that were far more productive than expected. NASA described one such discovery in 2012 as dramatic and unexpected, because scientists broke through thick sea ice and found waters rich in microscopic marine plants. Later work showed that under-ice blooms are not odd little exceptions. They have increasingly been observed in the Arctic as changes in the optical properties of sea ice allow more light to pass through. In other words, scientists looked beneath a frozen surface that seemed hostile to growth and found not emptiness, but one of the engines of the marine food web already hard at work. That matters because tiny plant-like organisms do not stay tiny in their consequences. They form the base of a much larger food web. Once you understand that sea ice provides habitat for primary producers such as algae and plankton, the whole region looks different. It is no longer just ice covering water. It is a structured environment with living material built right into it. NASA notes that sea ice is an important part of polar ecosystems, providing habitat for primary producers, while NSIDC explains that sea ice helps regulate exchanges of heat, moisture, and salinity, and influences ocean circulation as well. So beneath and within what looks like a white sheet, scientists found both insulation and habitat, both physical control and biological opportunity. That double role is part of why sea ice loss is so serious. You're not simply removing frozen water, you're stripping away structure from a system that depends on it. Then there was the sound. This is one of the more unsettling findings because it works directly against the human instinct to imagine the Arctic as mute. NOAA's work on the Arctic marine soundscape shows that the ice-covered Arctic can be among the quietest ocean environments in terms of background wave noise because ice damps the usual wind-driven surface sound. But the same ice also creates its own noises through formation, deformation, pressure ridging, and cracking. Add marine mammals, underwater earthquakes, ships, and changing open water conditions, and the result is a soundscape that is not empty at all. It is full of signals. Scientists listening beneath the ice found a world of groans, snaps, calls, and rising human noise. That discovery matters because animals such as whales depend on sound for navigation and communication, and as open water periods lengthen, the Arctic underwater acoustic environment is changing too. So even in darkness, even when the eye sees very little, the Arctic remains busy enough to be heard. Once researchers started mapping more of the seafloor beneath the Arctic Ocean, they found another reason to feel uneasy. The bottom of this ocean was, until surprisingly recently, far less well mapped than many people would expect for such an important part of the planet. The International Bathymetric Chart of the Arctic Ocean, version 5.0, notes that bathymetric mapping in the central Arctic has been especially difficult because perennial sea ice restricts the ships and vehicles that can collect data. Even now, despite major advances, the same project says that only a bit more than a quarter of the Arctic Ocean has been mapped with individual depth soundings under its criteria. That means scientists have spent years studying a region tied to global climate, while still improving the most basic picture of what the seafloor actually looks like. If that sounds mildly troubling, that is because it is. Humanity does enjoy discussing global systems before fully checking the floor plan, and the seafloor itself turned out to matter more than people once imagined. NASA material on seafloor control over sea ice notes that bathymetry helps control the distribution and mixing of warm and cold waters, which in turn affects sea ice patterns at the surface. In other words, the shape of the hidden bottom influences the behaviour of the visible top. Ridges, basins, shelves, and channels are not passive scenery. They guide water masses, affect where heat can go, and shape biological habitats. So one of the things scientists found beneath the Arctic ice was not just water and sediment, but a whole submerged architecture capable of steering the conditions above it. That sort of discovery has a way of humbling people, especially people who had been treating the Arctic as a flat white cap on a globe instead of a three-dimensional system, with a memory and a skeleton. Researchers also found methane escaping from some Arctic seafloor areas, especially around regions such as the western Svalbard margin. Here, the story becomes more complex than the more dramatic versions usually heard outside science. Methane seeps matter because methane is a potent greenhouse gas, and the thought of methane leaving the seafloor beneath a warming Arctic naturally gets attention. But detailed measurements show that the path from seabed to atmosphere is not always direct. A USGS-led study near Svalbard found that, in the waters they examined, the near-surface ocean absorbed far more carbon dioxide from the atmosphere than methane escaped into the atmosphere from the same waters, and the researchers emphasised that what happens depends on depth, chemistry, and local conditions. So scientists found methane seeps, yes, but they also found that the story is not a simple one of every bubble marching straight upward to ruin everyone's week. The Arctic is often more complicated than its headlines, which is somehow both reassuring and exhausting. There were biological surprises almost everywhere researchers looked carefully. The Arctic had long been described in language that made it sound nearly sterile for much of the year, but close study kept revealing living systems that were more active and more adaptable than expected. Ice algae cling to the lower surfaces and channels of sea ice. Zooplankton respond to bursts of food when light and nutrients line up. Bottom communities on shelves feed on organic matter that sinks from above. In some regions, productivity has risen significantly as sea ice has declined and open water seasons have changed. NOAA's 2025 Arctic Report Card notes that phytoplankton productivity increased markedly over the past couple of decades in several Arctic regions, with 2025 higher than the 2003 to 2022 average in 8 of 9 regions they assessed. That does not mean everything is thriving in a cheerful and balanced way. It means the biological engine is shifting, and shifts at the base of a food web tend to travel upward with consequences. Scientists found more life than expected, but they also found that change is already reshaping where, when, and how that life appears. The old picture of the Arctic as a place defined only by lack of warmth, lack of light, lack of species, began to break down with each expedition. Instead, what emerged was a place defined by timing. There is a right moment for light under thinning ice, a right moment for a bloom, a right moment for zooplankton to feed, fish to arrive, birds to hunt, seals to breed, whales to pass through. The danger scientists found was not simply that the Arctic is changing. It is that many of its living systems rely on timing so closely that even modest shifts can throw off the sequence. That is one reason changes beneath the ice matter so much. If the first signs of disruption appear in bloom timing, nutrient availability, stratification, or under ice habitat, the effects may travel outward before most people ever realize the first piece moved. Scientists also found that the ocean beneath the ice is much less isolated from the rest of the world than the frozen surface suggests. Water enters from the Atlantic and Pacific. Rivers deliver fresh water and sediments from land. Sea ice forms and rejects salt into the water below, increasing density and helping drive large-scale circulation. NSIDC explains that sea ice influences the ocean's global conveyor belt circulation by altering salinity and density. That means the Arctic is not simply a destination for cold water, it is part of the operating machinery of ocean circulation. What happens beneath the ice does not remain neatly beneath the ice. It participates in flows that connect regions, climates, and ecosystems far beyond the polar basin. So when scientists found hidden heat, changing salinity structure, and shifting circulation patterns there, they were not discovering local trivia. They were uncovering changes in a system that helps organize conditions elsewhere. One especially uncomfortable finding is how fast some of these changes are arriving. The oldest, thickest Arctic sea ice has declined by more than 95% since the 1980s, according to NOAA's 2025 report, and multi-year ice is now mostly confined to the area north of Greenland and the Canadian archipelago. Regions that are ice-free in August have warmed since 1982, and some Arctic marginal seas in the Atlantic sector saw extremely high temperature anomalies in August 2025. When scientists compare these long records with what they find beneath the ice, a pattern becomes harder to ignore. The old buffering system is weakening. The cover is thinner. The underlying ocean is more exposed. The warm influence from lower latitudes is pushing farther in. The Arctic is not merely losing ice at the top. It is being reorganized from below and from within. And that may be the most important thing researchers have found. Not one single monster, not one giant crack that explains everything, not one simple object on the seafloor that made the whole field gasp and spill coffee onto a stack of grant forms. What they found was a pattern, hidden warmth beneath fresher surface layers, greater biological productivity in places once assumed too dim or too sealed for large blooms, a soundscape shaped by cracking ice, whales, waves, and a growing human footprint, a seafloor still being mapped, yet already known to influence currents and ice from below, methane seeps that are real, but whose consequences depend on process and place, a system that looks hard and still from above, but underneath is layered, active, noisy, and increasingly unstable in ways that matter far beyond the Arctic. This is why polar scientists often sound more careful than dramatic, even when the findings are genuinely alarming. The Arctic does not usually hand over its truths in one cinematic reveal. It yields them in measurements, in temperature profiles, in acoustic records, in chlorophyll readings, in sonar maps, in the shape of a ridge, in a mooring that came back with data nobody was entirely hoping to see. Piece by piece, the picture beneath the ice became clearer, and what that picture showed was not a dormant ocean waiting patiently under a crust of winter. It showed a region that had been busy all along, and is now becoming busier in ways that are harder to predict. Because the more scientists found there, the less the Arctic resembled a frozen ending to the map. It began to look like a hidden operating room for the climate, one with dim lighting, strange noises, moving parts, and several instruments already blinking in ways that no one can afford to ignore. And once that realization set in, the next problem became unavoidable. It was not just what was under the ice. It was what that underworld sounded like when pressure built, when the surface cracked, and when the frozen ceiling above it stopped behaving like a ceiling at all. The Arctic sounds wrong to people who have never heard it properly. That may be the simplest way to begin. On the surface, the region looks like it ought to be one of the quietest places on Earth. A frozen sea, a lid of ice, long darkness, very little visible movement, and the general impression that even noise would rather stay indoors. From a distance, it invites the oldest mistake humans make about the far north, which is to confuse stillness with silence. Scientists learned very quickly that these are not the same thing at all. In fact, some of the most revealing things beneath the Arctic ice are not seen first, they are heard. That discovery changed the emotional feel of the region as much as the scientific one. It is one thing to study a place that looks empty. It is another to realise that the empty place has been talking the whole time. The underwater Arctic has a soundscape, which means a full acoustic environment made of natural sounds, animal sounds, and human-made sounds layered together. NOAA describes the Arctic marine soundscape as shaped by wind, waves, underwater earthquakes, marine animals, and especially sea ice, which is unusual because it can both dampen noise from the atmosphere and generate noise of its own through formation, deformation, ridging, and cracking. That makes the Arctic strange from the start. In some conditions, it is among the quietest parts of the ocean. In others, it becomes busy, sharp, metallic, groaning, and alive with sudden energy. There is something almost rude about that combination. The ice quiets the surface world by suppressing the usual noise of wind-driven waves, which means the ice-covered Arctic can have some of the lowest ambient sound levels in the ocean. But the same ice is never fully passive. When it forms, rubs, bends, fractures, or piles into pressure ridges, it adds sound back into the water in a different way. So the frozen surface is not a soft blanket thrown over the sea, it is more like a rigid ceiling that occasionally clears its throat, drags furniture across the floor, and reminds everyone below that it is under stress. Scientists listening through hydrophones do not hear one simple silence. They hear a place where quiet and violence can alternate with almost no warning. And because sound travels so well underwater, those noises do not stay politely local. In water, sound moves faster and over greater distances than it does in air, and in parts of the Arctic, layering in the water creates acoustic conditions that can guide sound remarkably far. Woods Hole. Oceanographic Institution describes an Arctic sound duct in the Western Arctic Ocean, where sound signals can stay trapped within a cold channel and travel as far as 250 miles. That means an underwater sound in the Arctic is not always a small private event. A crack, a ship, an animal call, a pulse from a distant source may travel through the system much farther than instinct suggests. A human listener standing above the ice may feel alone. The ocean underneath may be passing messages across distances that would seem absurd if the medium were air. Once scientists began listening more carefully, one of the first things they found was that sea ice has a voice of its own, and it is not especially soothing. There are snaps from sudden cracking, scraping sounds from ice rubbing against ice, grinding from flows pushed together by wind and current, and the deeper disturbances of pressure ridging when slabs collide and one is forced upward or downward. NOAA's Arctic Soundscape work notes that the dynamics of sea ice can greatly increase ambient sound levels across a broad range of frequencies. This matters scientifically because the sound reveals motion and stress that the eye cannot always detect, especially during darkness or bad weather. It also matters psychologically because once you know the ice is constantly speaking through strain, the whole region feels less like a frozen plain and more like an active structure carrying weight it would prefer not to discuss. There is a very particular discomfort in that kind of sound. Not the theatrical kind, not the sort of thing that belongs in a haunted house hallway with poor wiring, but a mechanical unease, a sense that the roof is under load, that the world overhead is not steady, only temporarily arranged. People who work in the Arctic grow used to many things, but few of them ever truly enjoy the sound of ice under pressure. It carries information, yes, but it also carries warning. It tells you that the frozen surface is dynamic, that stress is moving through it, that the map in your head may already be outdated. For scientists, that means the acoustic record is not just atmospheric background, it is evidence. It is a running logbook of strain, drift, contact, and change. Then there are the animals, which make the whole environment stranger in a different direction. NOAA notes that marine mammals are often the dominant biological contributors to the Arctic soundscape, and that many rely on sound more than other senses to navigate, find food, display reproductively, and communicate over long distances. Different species use different parts of the frequency range. Bowhead whales, belugas, narwhal seals, and walrus all occupy the acoustic space in their own ways. If you were expecting a frozen mute ocean, the discovery of all this sound is slightly humbling. You realise the Arctic was never truly silent. You were simply not equipped to notice the conversations. That idea that life under the ice is listening and speaking constantly changed how scientists interpret the region. Acoustic monitoring has revealed seasonal patterns in animal presence even when human observers are absent, and NIFA notes that these records have documented changes in the seasonal distribution of Arctic marine mammals. In the Pacific Arctic, bowhead whales have been detected in midwinter in the Beaufort Sea, and acoustic data show delayed autumn departures for bowhead and beluga whales from parts of the Beaufort and Chukchi seas. That does not mean every shift is fully understood or caused by one simple factor. It means the Arctic sound record is helping scientists detect biological change in a place where direct observation is often limited by ice, weather, darkness, or basic human reluctance to become a cautionary tale in a survival manual. Listening in the Arctic became one of the best ways to understand what could not easily be watched. A hydrophone left beneath the ice does not care whether the sun has set for months or whether a storm has erased the horizon. It keeps recording. It catches the groan of moving ice, the call of a whale, the intrusion of a vessel, the change in background conditions when open water expands. Over time, those recordings became a kind of diary written by the ocean itself. Not a neat diary, admittedly, more like a stack of audio notes from a region that speaks in cracks, whistles, pulses, choruses, and long stretches of uneasy waiting. Still, for researchers, it was one of the few ways to keep company with the Arctic when they physically could not be there. What made the soundscape more troubling in recent years was not only the presence of natural sound, but the arrival of more human sound in places that had historically been much quieter. NOAA's Arctic Soundscape Assessment points to cargo and fishing vessels as a persistent and growing source of anthropogenic noise, noting increased traffic on routes such as the Northern Sea Route, and a 44% increase in vessels using the Northwest Passage from 2013 to 2019. The Polar and Arctic Marine Environment Working Group, under the Arctic Council framework, goes further, describing underwater noise from shipping as a serious environmental problem for Arctic species and ecosystems. Its 2025 report says ship noise is projected to increase across the Arctic Ocean, including into the central Arctic Ocean, as sea ice extent and thickness decline and vessel traffic changes. That projection matters because the Arctic is not acoustically uniform. Some areas are already busy, others are naturally very quiet, and quiet places are often the ones most sensitive to added noise. The PAMI report describes parts of the high Arctic, including areas north of Greenland and eastern Canada, as among the quietest regions in the Arctic Ocean, and notes that by 2030, the Pan-Arctic acoustic environment is projected to see an average increase equivalent to almost quadrupling sound pressure because of diminished sea ice and increased vessel traffic. In places like the Chukchi Sea, the report found that areas very quiet in 2019 could increase by 40 decibels or more in modelled 2030 scenarios. That is not a subtle shift. That is a place-changing character. For marine mammals, that change is not cosmetic. NOAA notes that many human-made sounds overlap in frequency with the sounds marine mammals produce and hear, increasing the chance that important calls will be masked. Bowheads are especially sensitive to low frequencies, narwhals and belugas to higher ones, with seals and walrus occupying other bands in between. Studies from other oceans have already shown that ship passages can reduce communication range and elevate stress. In the Arctic, where animals rely so heavily on acoustic awareness, a noisier environment can interfere with navigation, communication, feeding, and reproduction. This is one reason the idea of opening the Arctic to more activity does not sound very cheerful to scientists. What often opens first is not merely water. It is the door to more disturbance. Some of the direct observations are hard to forget. The Arctic Council reported in 2025 that beluga whales have been observed fleeing from an ice-breaking ship at distances of 30 to 50 kilometres and then staying away from the area for several days. The same account notes walrus changing their behaviour by diving more and moving away from the source. These are not minor reactions. They are reminders that in the Arctic, sound can become a force that rearranges animal movement over large distances. When a machine arrives in a place built around listening, it does not need to touch anything to change the day. There is also a more subtle change happening as sea ice declines. Ice cover once damped much of the wind-driven surface noise that open water allows. NOAA explains that under open water conditions, increasing wind speeds are directly linked to increasing ambient sound levels, and sound levels can be many times higher under open water than under heavy ice. So even before ships arrive, a more open Arctic can simply be a louder Arctic, because waves and weather have more room to work. That means the soundscape is being altered from two directions at once. The loss of ice changes the physical acoustic environment naturally, and greater accessibility increases the likelihood of human noise on top of that. Scientists are not just hearing more vessels, they are hearing the basic background conditions of the ocean being rewritten. This is one of those moments where the Arctic becomes especially unsettling because the mechanism is so ordinary. Nothing supernatural is required. You remove ice, open water expands, wind has more influence, waves add sound, shipping becomes easier, engines add more sound. Animals that depend on hearing face a more crowded acoustic world. Scientists deploy more recorders because the old assumptions no longer hold. There is no villain twirling a moustache on the bridge of an icebreaker. There is only physics, access, and consequences, which is often a much less comfortable story because it refuses to stay inside one dramatic scene. The soundscape also matters because it can reveal changes before photographs do. A camera may show you the surface condition at one moment. An acoustic record can capture the rhythm of breakup, the arrival of whales, the passing of ships, the timing of storms, the persistence of open water, and the broad acoustic fingerprint of a place over months or years. In a region where direct access is costly and seasonal, that is invaluable. Scientists do not listen to the Arctic because it is charming, though it occasionally is in a severe sort of way. They listen because sound travels far, records stress, traces presence, and exposes patterns hidden by darkness and ice. The Arctic, for long stretches, is easier to hear than to see, and yet hearing it more clearly has not made it less disturbing. Quite the opposite. The more researchers learned, the less plausible the old idea of a blank dormant north became. Beneath the surface was a world of cracking ice, migrating whales, seal calls, pressure events, storm influence, distant engines, and shifting human access. The frozen top of the world was not a mute lid resting on dead water. It was a strained ceiling over an ocean that keeps speaking even in darkness. Every new recording reinforced the same lesson. What looks still may be under stress. What looks empty may be full of life. What looks quiet may only be quiet until the next fracture runs through it. That is why the strange sounds under the Arctic ice matter so much to scientists. They are not atmospheric flavour. They are not a curiosity you add to a documentary so the audience feels pleasantly unnerved before the ad break. They are evidence that the region is active, connected, pressured, and changing. They reveal how the ice moves, how animals use the habitat, how ships alter the environment, and how the loss of ice can transform even the basic background noise of the sea. And once you understand that the Arctic is full of these hidden messages, the next step becomes unavoidable, because sound is only one sign of the forces at work there. The real unease begins when you follow those sounds back to what is creating them: the pressure, the fractures, and the moving darkness that never stops shifting overhead. And this is where the Arctic begins to feel less like a landscape, and more like a shifting structure that never actually settles. The ice overhead is not a ceiling in the ordinary sense. It is a moving cover made of separate flows, frozen seams, weak zones, old ridges, new fractures, and thin sections that can behave very differently from one day to the next. Even in the darkest part of winter, when common sense would like to imagine everything locked in place, the ice is still travelling under the push of winds and ocean currents. NSIDC's own Arctic snapshot puts it very plainly. Even in the dark of polar winter, sea ice is constantly on the move. That single fact changes the mood of the whole place. It means the frozen surface is not ground, it is traffic. Slow traffic, sometimes chaotic traffic, but traffic all the same. Beneath the darkness, the Arctic is always rearranging itself. That motion matters because drifting sea ice does not glide around gently like a polite tray on a dining table. It collides, it twists, it shears, it pulls apart. The Arctic pack is a broad field of ice flows, and those flows are driven by wind, ocean currents, and tides into constant interaction. When the ice spreads apart, it opens leads, which are strips of exposed ocean. When it converges, the flows pile into one another and build pressure ridges. A cryosphere review in the cryosphere describes lids and ridges as dominant features of Arctic sea ice that affect heat loss and surface drag and arise from the brittle deformation of the ice pack. Those features can stretch from a few meters to hundreds of kilometers. In other words, the frozen surface is not one unbroken sheet, so much as a field of fault lines and impact zones, constantly drawn and redrawn by force. Pressure ridges are especially unnerving once you understand what they really are. From above, a ridge may look like a rough raised line in the snow, the sort of feature a tired person might regard as mildly inconvenient, and then regret underestimating for several hours. But most of a ridge is not above the water at all. NSIDC explains that when sea ice bends or fractures and piles on top of itself, it forms ridges with a surface sail and a much larger underwater keel, and the keel is roughly 9 times thicker than the visible part. In the Arctic, these ridges can reach around 20 meters in thickness when thick ice deforms. That means a ridge is less like a wrinkle and more like a submerged barricade. It changes drag, changes habitat, changes snow accumulation, and changes what can move where. Scientists looking at the Arctic do not just see broken ice. They see a whole rough architecture of stress built into the surface and hidden below it. The darkness makes all of this worse, not because the physical processes become more active at night, but because they become harder to read. In polar regions, visible satellite sensors can only collect data during the daytime, and NSIDC notes that this is a major problem for measuring sea ice in places where darkness prevails. Clouds make it even harder by obscuring ice 70 to 90% of the time in many polar conditions. So one of the odd realities of the Arctic is that a place already difficult to work in also spends long periods making itself difficult to see. The ice moves anyway, the lead's still open, the ridges still build, the surface still cracks. Yet for long stretches, the most obvious human way of tracking a landscape, simply looking at it, becomes unreliable. That is part of why the region feels so hostile to certainty. It keeps changing when observation is least convenient. Researchers who have lived on the ice have described this in ways that are far more vivid than any simple climate graphic. During the Mosaic expedition, scientists deliberately froze the icebreaker polar stern into a large floe and let it drift across the central Arctic for a year so they could observe the system through all seasons, including polar night. The chosen floe was several kilometres wide and thick enough to support a full research camp, but even then the surface refused to behave like stable ground. Brookhaven's official Mosaic updates recorded that new cracks and pressure ridges appeared in the ice in the middle of a power line running across the camp, and other entries noted that the team was racing the loss of daylight, because within days the sun would no longer rise above the horizon. That is a remarkable image when you stop to picture it properly. Scientists build an observatory on what seems like a solid frozen platform, and the platform begins changing shape around their cables and instruments while winter darkness closes in. That sort of experience helps explain why sea ice researchers rarely speak about the pack as though it was simply melting or freezing. They talk instead about dynamics, deformation, age, thickness, drift, roughness, convergence, divergence, and regime change, because the ice is a mechanical system as much as a frozen one. The Norwegian Polar Institute's N-Ice 2015 project was designed specifically to understand how the rapid shift toward younger and thinner sea ice is affecting energy fluxes, sea ice dynamics, the ice-associated ecosystem, and climate more broadly. Their project summary makes a very sharp point. The older multi-year ice that used to dominate much of the Arctic has been largely replaced by younger ice, and that raises a basic question about whether the system is still functioning the way earlier observations assumed. That is a careful scientific way of saying the Arctic may now obey somewhat different practical rules than the ones many experts learned on. NOAA's 2025 Arctic Report Card reinforces that concern. It states that by the end of summer 2025, Arctic sea ice was younger, thinner, and 28% less extensive than in 2005, and that these changes are opening the region to more human activity, while increasing concerns about safety, security, and the environment. That matters here because younger, thinner ice does not simply disappear faster in summer. It also behaves differently while it is present. It tends to be more vulnerable, less durable, and more responsive to wind and stress. A thinner system can shift faster, fracture more easily, and offer less confidence to anyone trying to work on it, cross it, or model its future. The fear is not only that there is less ice, it is that the ice that remains may be more restless. The picture becomes more complicated, and in some ways more troubling, when scientists look at the roughness of the ice itself. A 2025 study in Nature Climate Change found evidence that the Arctic is becoming smoother overall, with fewer pressure ridges and reduced surface drag because of the loss of old ice. At the same time, the same study emphasises that the sea ice cover is becoming more dynamic, meaning faster and more seasonally dominated, and that seasonal ice can be more susceptible to deformation. So the Arctic is not heading toward a simple future of either more ridges or fewer ridges everywhere. It is heading toward a system in which the old, thick, heavily deformed ice declines, while a more mobile, younger cover responds differently to wind and current. That is exactly the sort of change that bothers scientists because it means long-standing surface cues and physical expectations may stop being reliable guides. The landscape can look smoother and still be mechanically less trustworthy. Leads make that instability visible in a harsher way. When sea ice breaks apart and a lead opens, Dark water is suddenly exposed to frigid air. The cryosphere notes that strong upward heat flux occurs from the relatively warm ocean to the cold atmosphere through these openings, promoting new ice formation and altering albedo. A lead, then, is not merely a crack, it is an exchange point, a narrow wound in the cover where the atmosphere and ocean suddenly touch more directly. It releases heat, grows new ice, shifts local conditions, and may later close again under converging motion. Some leads remain openings for a while, others partially close, some may evolve into ridges. The feature itself is not always permanent, but the process is constant. A frozen ocean that keeps tearing itself open in long lines of exposed water is never going to feel entirely settled, especially when those lines can form in darkness and move with the broader ice pack. The darkness adds another practical problem that people outside polar work rarely think about. Moving through the Arctic pack is difficult enough in daylight, but under polar night conditions the visual field narrows, depth becomes harder to judge, weather can flatten the horizon, and what looked usable a few hours earlier may no longer be usable at all. The official mosaic material from Brookhaven describes how the team was working against the clock as daylight vanished, and later documented that the camp's infrastructure had to adapt to new cracks and ridges. That may sound like an operational inconvenience, but it is more than that. It is a reminder that the frozen world is not merely hard to observe, it is hard to trust. Every camp, every measurement station, every route over the ice depends on a temporary agreement with a surface that is still under stress. In ordinary life, people are not used to the ground renegotiating the terms of use while they stand on it. There is also a wider mechanical story unfolding across the basin. The Mosaic expedition was built around the reality of the transpolar drift, the broad conveyor that carries sea ice from the Siberian side of the Arctic across the central basin toward Fram Strait. While other ice can circulate for years in the Beaufort Gyre north of Alaska and Canada, the fact that researchers could freeze into a flow and let it carry them along these pathways was scientifically brilliant and emotionally unnerving for exactly the same reason. It demonstrated that what seems like a fixed field of ice is actually a transport system. The flows move, the ridges travel with them, the fracture zones evolve, and even thick multi-year ice is part of a circulation pattern. When you stand in the Arctic, you're often standing on something in transit. All of this helps explain why scientists sometimes describe the central Arctic in winter almost like a working industrial site without the courtesy lights. The machinery is there, loads are moving through it, surfaces shift, weak zones open, thick blocks collide, hidden keels drag below the waterline. Winds can rearrange broad areas of ice in a short period. The ice may look white and simple from high above, but at human scale it is a field of mechanical events. Older expedition logs and modern measurement programs both return to the same reality. The Arctic pack is not a neat frozen plate. It is a brittle composite material spread over a moving ocean, and brittle materials behave in bursts. Long tension, then sudden failure. Compression, then piling. Separation, then refreezing. One reason the place feels so severe is that these changes are often not gradual in the moment. They can happen quickly enough to turn routine work into route planning into delay, and delay into risk. That severity would be easier to accept if the Arctic were staying the same overall, but the evidence points the other way. NOAA's 2025 Sea Ice Summary says the profound changes in sea ice since 2005 are bringing new concerns about safety and human activity, while a NICE 2015 stressed that the system has changed so rapidly that observations from an earlier era may no longer describe current conditions well. This is one of the reasons scientists sound uneasy rather than merely fascinated. They are not studying a difficult environment that has held its shape. They are studying a difficult environment whose basic material character is shifting while they try to measure it. In one sense, the Arctic has always been a world of pressure, cracks, and moving darkness. In another sense, The balance among those things is changing now, and not in a way that makes the work easier or the future clearer. There is a final detail here that makes the whole setting even stranger. Pressure ridges are not only obstacles, they're also habitat. The 2025 Nature Climate Change study notes that ridge keels shelter ice-associated organisms across trophic levels and enhance turbulent mixing that can support more biomass than surrounding level ice. So the very features that make travel difficult and signal intense mechanical stress also create living structure in the ice-ocean system. That is classic Arctic logic. The dangerous parts are often the biologically useful parts. The roughness that threatens equipment can also support life. The fracture that opens heat exchange can also alter access to light and food. This is not a world where physical violence and ecological function are neatly separated. They overlap. That overlap is one reason scientists cannot dismiss the Arctic as simply hostile. It is hostile, yes, but it is also productive, inhabited, and full of living things that have learned to use the instability. And that, in the end, is what makes the darkness above the Arctic Ocean feel so different from ordinary night. It is not empty darkness. It is darkness moving over a surface under load, over cracks that may open and close, over ridges whose bulk hides below the waterline, over flows that drift across the basin, over camps that must keep adapting, over a younger and thinner ice cover that no longer behaves quite like the older one it is replacing. Scientists do not fear this place because it is silent or dead. They fear it because it is active in ways that are difficult to predict and hard to observe at the exact moments when prediction would be most useful. The frozen ceiling keeps shifting, and underneath it life has gone on learning the rules. That is where the next part of the story begins, because in a place this dark, this cold and this unstable, some of the most surprising discoveries are not about the ice at all, but about the creatures that have managed to live beneath it. What makes the Arctic especially unsettling is that once you accept the ice is moving, cracking and groaning overhead, the next surprise is discovering that the water beneath it is not just occupied, but crowded with specialists. Not crowded in the tropical sense, of course. No riot of coral colours, no fish behaving like overexcited parade confetti, no reef making a public spectacle of itself. The Arctic prefers a quieter style. Its abundance hides in the dim, in the narrow season, in the under-ice film, in the life forms that survive by being efficient, well-insulated, very patient, or in some cases so chemically and physically adapted to the cold that they seem less like ordinary animals and more like living rebuttals to human assumptions. The frozen ocean looks like a place where almost nothing should work, and yet a great deal does. Sea ice itself is habitat, not just a lid, and official sources from NSIDC and NOAA both emphasise that life thrives above, below, and within it, with the ice offering a platform for algae and an essential habitat for marine life. The whole arrangement begins with organisms so small that most people would never guess they help hold up the entire Arctic food web. Algae grow in and under sea ice, especially along the lower ice surface, where enough light can reach them in spring. NSIDC explains that sea ice offers a platform for algae to grow, and when the ice melts, those algae enter the sea and help fuel blooms of phytoplankton, which form the foundation of the marine food chain. NOAA's polar environment pages describe ice algae as a very important part of the marine food web, and NASA's under-ice bloom work showed that scientists punching through thick sea ice found waters rich in microscopic marine plants in places once assumed too sealed and dim for that level of productivity. That discovery was startling because it overturned a comfortable old assumption. The under-ice world was not merely enduring winter and waiting for better conditions. In places, it was already hard at work converting light into food at the exact moment humans were still peering at the surface and assuming the system must be half asleep. And that small beginning matters because the Arctic is built on timing. Ice algae appear early, often before open water phytoplankton blooms fully take over, which means they can feed animals at a crucial seasonal moment. NOAA Fisheries notes that when sea ice melts and retreats, ice algae is released into the water, and in cold years the timing can favour cold-adapted zooplankton species such as Calanus glacialis. In warm years, when ice retreats early, that timing can be wrong for them. There is an almost bureaucratic cruelty to this, really. Not enough that the organisms must survive in darkness and cold, they must also keep perfect time in an environment where the calendar itself is beginning to misbehave. Many Arctic creatures do not just need food, they need the right food at the right moment, often after months of scarcity. Shift the schedule, and the whole elegant arrangement starts fumbling for its notes. That brings us to the zooplankton, one of those words that sounds technical until you realise it includes some of the most important little creatures in the sea. Copepods, for instance, are tiny drifting crustaceans, but in the Arctic they function like biological batteries. Large, high-fat copepods are especially valuable because they store energy that larger animals can tap into by eating them directly or by eating something that already has. NOAA Fisheries reported in 2023 that in the northern Bering Sea, loss of sea ice was linked to dramatic shifts in zooplankton communities, with large, high-fat copepods dwindling, while smaller zooplankton expanded in number and range. Fisheries and Oceans Canada also describes copepods and Arctic cod as forage species that are important food for many fish, marine mammals and birds, noting that larger, more nutritious adults are preferred by large predators. It is a very Arctic detail that one of the great struggles of the food web comes down to whether the tiny drifting snacks are big enough and fatty enough to keep the rest of the system running. This is survival by calories, not by drama. Once those copepods and similar prey are in play, the next level of the Arctic strange community begins to appear. Arctic cod are among the most important fish in this system, and the official descriptions of them are so consistently central that they almost sound like the quiet middle managers of the whole region. NOAA Fisheries calls Arctic cod a key component of the Arctic marine ecosystem, and notes that they are an important food source for seabirds, ringed seals, narwhals, belugas, and other fish. Fisheries and Oceans. Canada likewise describes Arctic cod as a key forage species serving as prey for numerous marine animals, while broader Canadian Arctic ecosystem reporting highlights consistent trends in zooplankton and Arctic cod because of their importance to the food web. This is one of the reasons scientists care so much about a fish the average person could probably walk past in a biology textbook without ceremony. Arctic cod turn microscopic productivity into something larger predators can actually use. They are one of the main ways the energy stored in algae and zooplankton gets moved upward through the system. If Arctic cod struggle, many things notice. They also happen to be strongly tied to the conditions people are busy changing. NOAA Fisheries reported that Arctic cod may be among the cod species most vulnerable to warming ocean waters, and NOAA's 2024 Arctic report card says ringed seal diets in the Pacific Arctic are shifting from Arctic cod towards saffron cod as waters warm. That is a sobering little change because diets are often where ecosystem stories become easiest to read. Long before the public follows a paper on stratification or primary production, the seals are already rearranging the menu. It is one thing to say the Arctic is warming. It is another to see that change show up in the stomach contents of an animal that has been living on the sea ice longer than any government policy has been pretending to manage it. The creatures there do not wait for perfect certainty. They adjust, move, starve, or switch prey according to what the water offers. Scientists reading those shifts can see the system leaning in a new direction before many outsiders realize the floor has tilted at all. The seals themselves are among the clearest examples of Arctic life existing exactly where common sense says conditions should be unreasonable. 4 species of ice seals occupy the Bering, Chukchi and Beaufort Seas west and north of Alaska, according to NOAA's 2024 report, and ringed and bearded seals were listed as threatened under the Endangered Species Act in 2012 because of concern over predicted sea ice decline. Yet the same NOAA reporting says these populations in the Pacific Arctic currently remain healthy, with no sustained change in body condition evident from long-term subsistence monitoring. even as the environment around them changes rapidly. That is worth pausing over. The Arctic is not populated by fragile ornaments waiting to shatter on cue. Many of these animals are resilient, practiced, and deeply adapted to the cold. A ringed seal pup on the ice is not cute by accident. It is the product of a system that evolved to use sea ice for resting, breeding, avoiding predators, and accessing prey below. The problem is not that Arctic animals are weak. The problem is that they are adapted to a world with certain rules, and those rules are being revised faster than scientists are comfortable with. Farther up the scale, whales make the place stranger still. Bowhead whales are one of the few whale species that live almost entirely in Arctic and subarctic waters with seasonal sea ice, according to NOAA Fisheries, and are among the large whales most adapted to icy water, carrying blubber that can reach roughly 1.6 feet thick. Narwhals, NOAA notes, are found in the Arctic Ocean and live year-round north of 60 degrees latitude, primarily in the Canadian Arctic, Hudson Bay and Baffin Bay. These are not tropical visitors wearing the wrong clothes. These are specialists. Bowheads can use ice-covered areas even in winter, and case studies from Canada's Arctic seas point to Arctic cod as a primary prey species for belugas in offshore marine waters. So when people imagine the Arctic as empty, what they miss is that some of the most distinctive marine mammals on Earth are not merely passing through. They are built for the place. They listen through it, feed through it, navigate through shifting ice and darkness as though the rest of us are the ones poorly adapted, which, to be fair, we are. A human in the Arctic needs planning, insulated boots, emergency systems, and usually a very persuasive grant proposal. A narwhal needs to get on with its day. Still, perhaps the creature that best captures the mood of this hidden world is the Greenland shark, partly because it seems to have arrived from a less hurried era, and partly because it sounds like something invented by a novelist who had become tired of ordinary sharks. NOAA Ocean Service says scientists estimate Greenland sharks live at least 250 years and may live more than 500. Fisheries and Oceans Canada describes them as the only shark species regularly found in these very cold Arctic and subarctic waters, inhabiting temperatures between about -2 and 7 degrees Celsius, usually at depth but sometimes near the surface in winter and around ice edges. They are large, slow and mysterious, and much of what scientists know about them has been hard-won because they live where observation is difficult. There is a special kind of Arctic logic in having one of the longest-lived vertebrates on Earth moving through dim, frigid water beneath ice. Of course, there is a shark down there that may have begun life centuries before modern climate science existed. Of course, the frozen ocean keeps a patient witness. The place has a talent for making the living world feel older and less impressed by us than we would prefer. Yet the Arctic does not reserve its surprises for charismatic animals with names people remember. One of the more humbling findings in recent Canadian reporting is that biodiversity on the seafloor of the Canadian Arctic Ocean can be higher than in Canadian Atlantic and Pacific waters, contradicting the widespread assumption that biodiversity simply declines the farther north one goes. That point from Fisheries and Oceans Canada's 2025 ecosystem reporting is quietly astonishing. It means that beneath the ice, on the bottom, in the cold and dark and pressure, there are communities of invertebrates diverse enough to overturn a very common mental picture of the North as biologically stripped down. Official Canadian reporting also notes that algae released from sea ice can be quickly eaten by grazers in the water and by invertebrates on the sea floor, which reminds us that the bottom is not separate from the ice above. Food falls, life responds. The surface season writes consequences onto the seabed. The Arctic is vertically connected in a way many people never imagine. What grows under the ice can feed what crawls in the sediment far below. There is another reason these creatures matter so much. They are not just inhabitants of an extreme place. They are evidence of how that place works. Ice algae tell scientists whether the seasonal handoff between ice and open water is changing. Zooplankton shifts reveal what happens when sea ice loss alters bloom timing and ocean conditions. Arctic cod serve as a kind of ecosystem messenger. because they respond quickly to temperature and ice extent, as NOAA has noted in earlier Arctic reporting. Ringed seal diets show how warming waters and changing prey availability travel up the food web. Bowhead whales sample the ecosystem at large scales, and NOAA in 2025 reported that bowhead whale samples are even helping track rising algal toxins linked to warming waters in Arctic food webs. The animals beneath the ice are not just surviving, they are reporting in their own biological way on the state of the system. Scientists read their condition, their range, their diet, their reproduction, their sounds, and their absence as signs. In the Arctic, wildlife is not merely something to admire from a distance. It is part of the monitoring network, except the monitoring network swims, dives, molts, and occasionally weighs several tons. And this is where the emotional force of the Arctic really begins to settle in. These are not random oddities decorating a remote environment for the benefit of documentaries and souvenir calendars. They are linked. Sea ice supports algae. Algae feed zooplankton. Zooplankton feed fish. Fish feed seals, whales, birds, and larger predators. The seafloor receives the leftovers and builds its own living communities from what sinks. Official sources across NOAA, NSIDC, NASA, and Fisheries and Oceans, Canada, all point to the same broad reality. The Arctic marine ecosystem is tied closely to sea ice, timing, and cold-adapted species that have learned to use an environment most animals would find unworkable. Remove or weaken the structure, and the creatures do not simply vanish one by one in tidy order. The whole system begins to reorganize, sometimes subtly, sometimes abruptly. That is why researchers sound so careful. They are not describing a few hardy beasts clinging to the edge of survival. They are describing a complete working community that depends on conditions no longer guaranteed. So yes, the Arctic is full of creatures living where almost nothing should. But the deeper truth is that they do not merely tolerate that world, they define it. They turn ice into habitat, darkness into timing, cold into structure, and brief windows of light into an entire chain of nourishment that stretches from algae to whales. If the place feels eerie, it is partly because the life there is so competent. It has learned to work with narrow margins, moving ceilings, freezing water, and seasons that would seem impossible anywhere else. The more scientists study those creatures, the more they realize the Arctic is not a biological blank. It is a library of adaptations, many of them ancient in practical terms, all of them written into bodies that still carry the memory of a colder world. And once you start thinking of those animals that way, not just as residents but as records, it becomes very hard not to turn next toward the older traces the Arctic has been keeping in its ice, its sediments, and the seafloor beneath them. By the time scientists have spent enough time around the Arctic, they stop treating ice and seafloor as scenery and start treating them like storage. That is really what they are. Not storage in the simple sense of objects being kept somewhere cold until someone remembers to label the box, but storage of information. The Arctic keeps records. Snow falls, gets buried, and turns to ice. Dust settles. Ash from distant eruptions lands and is sealed away. Tiny bubbles trap old air. On the seafloor, shells, mud, plant fragments, minerals, and microscopic fossils settle layer by layer. Decade after decade, century after century, they build a physical archive of conditions that no person was there to watch. When scientists drill into Greenland ice or pull a long tube of mud from the Arctic seabed, they are not just collecting samples. They are opening files the planet has been keeping for a very long time. The ice archive is the one people tend to imagine first, and for good reason. NASA explains that ice sheets contain records of hundreds of thousands of years of past climate trapped in ancient snow, and the Greenland Ice Sheet Project 2 recovered a core 3,053.44 metres long, providing a record of at least the past 110,000 years. NOAA's Paleoclimatology Archive also includes Greenland ice core records spanning about 120,000 years in the NGRIP dataset. That is an astonishing thing when you stop and think about it properly. A frozen column drilled from Greenland can hold a climate history far older than agriculture, older than cities, older than writing, older than almost every story human beings tell about themselves with any confidence. We look at the Arctic and see a difficult place. Scientists look at it and also see a library written in compressed snow. What makes the ice so useful is not merely its age, but the number of different clues packed into it. NOAA's National Centres for Environmental Information notes that ice cores preserve proxy indicators such as oxygen isotopes, methane concentrations and dust. NASA adds that ice cores can provide records of temperature, precipitation, atmospheric composition, volcanic activity, and wind patterns, while trapped air bubbles preserve past atmospheric composition and particles such as dust, volcanic ash, smoke, and pollen. In other words, an ice core is not one measurement. It is an entire stack of measurements waiting to be read correctly. Some layers say something about temperature, others say something about the atmosphere, or distant eruptions, or how windy things were, or whether the air carried more dust at the time the snow fell. This is why ice core science can sound so technical, and still feel oddly intimate. It is literally old weather with the details left in. That trapped air, in particular, changed how scientists understood the past. NASA's summary of the ice core record states that air bubbles in the ice provide a record of past atmospheric composition, and that ice core records show current levels of carbon dioxide and methane are higher than any previous levels in the past 400,000 years. This is one of those findings that is simple enough to say in a sentence, and heavy enough to change how whole fields of science talk about the modern world. The Arctic does not only preserve old cold, it preserves old air. It lets scientists compare ancient atmospheres with the one we're living in now, and the comparison has not been especially reassuring. There is something unsettling about learning that a frozen sheet in Greenland can remember the chemistry of air, breathed by creatures and landscapes long gone, then quietly show that the present atmosphere is now outside the range of what those old layers recorded over immense spans of time. Even the physical condition of the Greenland core tells part of the story. NOAA's GISP 2 information notes that the summit region of Greenland was an ideal place for recovering a deep core, because the annual mean air temperature is extremely low and melt layers are minimal, helping preserve gaseous, soluble, and insoluble evidence of past environments. That matters because records are only useful if they survive. In warmer places, melt can blur or damage the archive. In central Greenland, cold helped lock it in. That is a very Arctic kind of irony. The same severe conditions that make the region difficult for humans also make it exceptionally good at remembering. Scientists do not just go north because it is remote. They go because the cold has been doing careful filing for tens of thousands of years, and the memories are not always what people expect. Many casual ideas about the Arctic assume it has always been more or less what it is now: cold, sparse, severe, with slight variations in unpleasantness. The geological record says otherwise. The first scientific drilling expedition to the Central Arctic Ocean, ASEX, reached the Lomonosov Ridge and recovered sediments that revealed a far older Arctic climate history, and later drilling plans for Expedition 377 were built specifically to recover a more complete long-term Cenozoic record from the same general region, because the Central Arctic Archive is so important for understanding the transition from an early Cenozoic greenhouse world to a later icehouse world. Scientists did not drill there because they expected a monotonous story. They drilled there because they suspected the Arctic had changed dramatically before and wanted proof layered in mud. They found it. A USGS summary of ACEX results reports that pollen preserved in these Arctic Ocean sediments indicates that during the late Paleocene, areas near the coring site supported mixed conifer hardwood forests including pine, spruce and walnut, and that bioclimatic analyses suggest mean annual temperatures around 13 degrees Celsius, with lipid biomarkers indicating about 14.6 degrees Celsius. During the Paleocene-Eocene thermal maximum, Broad-leaved swamp forests, including members of the cypress family and palms, dominated the nearby landscape, with mean annual temperatures rising by as much as 3.5 degrees Celsius. This is the sort of result that quietly rewires the brain. The modern Arctic trains people to expect moss, ice, dwarf shrubs, and the occasional argument with wind chill. The older Arctic, at certain times, supported forests and swamp vegetation in regions now associated with permafrost and pack ice. Beneath the frozen ocean, scientists found evidence that the far north had once been much warmer, greener, and biologically stranger than the modern imagination allows. The mud held even more specific surprises: ECORD's ACEX core. Replica description notes that mid-Eocene Arctic sediments include dark, organic-rich layers of azolla, a freshwater fern, alternating with microfossils such as diatoms, suggesting freshwater episodes in Arctic surface waters around 50 million years ago. That is an extraordinary clue. It means the Central Arctic Ocean was not always the salty, ice-dominated marine environment people instinctively imagine. At least in some intervals, the surface conditions were fresh enough to support an organism associated with freshwater settings. Scientists love findings like that because they force the whole reconstruction to become more precise. You can no longer say only, "it was warmer once." You have to say, the Arctic Ocean itself behaved differently enough that surface water conditions changed in ways modern maps do not prepare you for. That is the kind of secret the seafloor likes to keep until somebody drills into it. The Arctic seabed does not only preserve stories from tens of millions of years ago, it also stores shorter records that are useful exactly because they are detailed. USGS says sediment cores collected throughout the Arctic region can capture deposits up to 500,000 years old and allow scientists to reconstruct sea ice distribution from past centuries to millennia and beyond. In the Beaufort Sea, USGS researchers use microfossils from sediment cores to rebuild climate patterns, sea ice, circulation, and ecosystems over the past 2,000 years. That shorter scale is important because it helps bridge the gap between deep geological time and the relatively tiny slice represented by instruments and satellites. If an old core can show what happened over a few thousand years, and a thermometer record can show the past few decades, scientists can start joining the long story to the short one. The Arctic does not hand over one giant answer. It gives a layered set of records, each useful at a different time scale, and then there is the seafloor itself, not just what settles on it. Mapping beneath the Arctic has improved a great deal, but the newest IBCAO 5.0 release still reports that only about 25.5% of the seabed 2030 Arctic region is constrained by direct depth measurements, with North Greenland including part of the least mapped area of the Arctic Ocean. The same study says perennial sea ice remains a major obstacle to systematic data collection, and that complete mapping is still a significant challenge. This matters for more than cartographic neatness. A poorly mapped seafloor hides ridges, basins, sills, troughs and landforms that control circulation, influence ice behaviour, and preserve signs of earlier glaciations. So when scientists say the Arctic still holds secrets, they do not always mean metaphorical ones. Sometimes they mean, quite literally, that large parts of the floor remain only partly observed beneath a hostile surface cover. We are trying to read history in a room whose lights are still only half on. Where mapping has been done well, the seafloor has turned out to be a remarkable recorder of ice history. A nature communication study of Petermann Fjord and Nares Strait found submarine glacial landforms that preserve evidence of glacier retreat after the last glacial maximum, including a large grounding zone wedge showing that Petermann Glacier stabilised at the fjord mouth for a considerable time, likely buttressed by an ice shelf. The same study reports deeper iceberg plough marks indicating that thick grounded ice persisted to substantial water depths before final breakup. This is another very Arctic habit of evidence. The ice may be gone from a former position, but the bottom remembers where it was. A ridge, a plough mark, a streamlined groove on the seabed becomes a sentence in the history of ice advance. Pause. and collapse. Scientists do not need a human witness if the landform is still there. That seabed memory is especially important because instrumental records are so short. USGS says long-term paleoceanographic records from Arctic sediment cores are needed precisely because direct measurements only go back a few decades, while glaciers, sea ice and climate vary over much longer periods. This is one of the central difficulties in understanding the Arctic today. The region is changing very quickly, but the part of the record most familiar to the public is also extremely brief. Without ice cores and sediment cores, the conversation would be trapped inside modern memory, and modern memory is a terrible guide to systems that run on century and millennial scales. The old layers do not solve every problem, but they at least expand the frame. They remind scientists that the Arctic has shifted before, that ice margins have advanced and retreated, that ocean conditions have reorganized, and that the North has occupied states modern observers would barely recognize. Some of the records stored in sediment are not climatic in the usual sense at all. USGS reported in 2024 that cores from the Loki's Castle hydrothermal vent field northeast of Greenland preserved a sedimentary record of past hydrothermal activity more than 2,300 metres below the Arctic Ocean surface. The work found a surprising transition in sediment composition over short distances and an unexpected abundance of talc among the major hydrothermal minerals, forcing researchers to reconsider assumptions about what deep Arctic hydrothermal systems leave behind. This is a useful reminder that the Arctic seabed is not only a climate archive, it is also a geological one. It stores evidence of venting, mineral precipitation, mass wasting, and processes occurring far below the seafloor itself. Even under the coldest ocean, the Earth is still geologically busy. The Arctic keeps records of that too. What scientists eventually learn from all of this is that the Arctic has never been one thing for very long in geological terms. It has been colder and warmer, more ice-covered and less, more marine, at times strangely fresh at the surface, home to conditions suitable for forests in regions now locked in frost. The ice archives tell one part of that story by preserving air, dust, isotopes, and annual layering. The seafloor tells another by preserving mud, pollen, microfossils, plough marks, retreat ridges, mineral traces, and the shapes left by vanished ice. None of these records is perfect by itself. Ice can melt or deform. Sediment records can contain gaps, as ACX itself showed with a critical hiatus or interval of strongly reduced sedimentation across part of the Cenozoic sequence. But taken together, they form something powerful, a long and increasingly detailed account of a region that modern humans met in one of its colder moods, and then mistakenly assumed had always looked that way. And that is where the Arctic becomes most uncomfortable as a scientific subject. These ancient records are not just interesting because they are old, they are useful because they tell scientists what this system has been capable of. A warm Arctic with forests is not a myth, it is in the sediment. Freshwater episodes in the central Arctic are not a dramatic invention, they are in the core. Rapid changes in atmospheric composition are not guesses made by anxious people staring at model output. The evidence is in trapped air bubbles, in isotope ratios, in dust layers, in seafloor landforms, in microfossils, in the quiet persistence of the archive itself. The frozen north has changed before, sometimes profoundly, and the reason scientists keep drilling, mapping, and measuring is that the old record helps define the range of futures the Arctic might still be able to enter. So when we talk about ancient secrets locked in ice and seafloor, we are really talking about the Arctic refusing to let the present be the only version of itself that matters. It keeps older versions underneath, warm versions, freshened versions, glaciated versions, retreating versions, versions marked by different chemistry, different vegetation, different ocean structure, different ice geometry. That is why scientists keep coming back to the archives under the cold. They want to know not just what the Arctic is doing now, but what it has done before when pushed into other states. And once you sit with that long enough, another realization follows naturally. The Arctic is not only a record of cold, hidden inside those records, and sometimes still moving in the ocean today, is heat. And those older records in the ice and mud keep pointing to one uncomfortable fact. The Arctic has never been protected by cold alone. It has always been a place where heat matters, where the path heat takes matters even more, and where a region that looks frozen from above can still be carrying warmth in places most people never think to look. This is one of the reasons scientists speak so carefully about the Arctic Ocean. The cold is obvious. The heat is not. The cold is on the surface, in the photographs, in the air, in the public imagination. The heat is often under the surface, moving through layers, arriving from lower latitudes, building in summer, hiding beneath fresher water, or rising slowly from the seafloor. It is the kind of problem that would be easier to live with if it wore a brighter name tag. Instead, it tends to sit quietly underneath the ice, like a bad idea that has learned patience. The first part of that hidden warmth comes from the Atlantic itself. NOAA's 2025 Arctic report card describes warm, salty Atlantic water flowing northward into the Arctic Ocean at roughly 150 to 800 metres depth, beneath near-freezing, relatively fresh surface water, and beneath the halocline, the density stratified layer that has historically helped keep the deeper warmth from reaching the surface and the ice above it. For years, that halocline acted like a thermal barrier. Not a perfect one, but an effective one. Even after Atlantic water warmed by more than 1 degree Celsius in the 1990s and 2000s, the halocline largely insulated the surface and sea ice from that heat. Scientists took some comfort in that. The Arctic might be carrying extra heat below, but at least the upper structure was still doing its job. That comfort has not held up especially well. NOAA reports that in the Eurasian basin, the halocline had lost its fundamental role as an effective barrier by the mid-2000s, with about a 30% decline in stability over the preceding 3 decades. Increased upward heat transport from Atlantic water has already lowered regional rates of winter sea ice formation. That is not a subtle change. That is the Arctic's protective layering becoming less protective, while the heat beneath it remains very real. Once you understand that, the frozen surface starts looking different. It is no longer just ice being melted from above by warmer air and stronger sunlight. In some regions, it is also ice being weakened from below by an ocean that is carrying more warmth than it used to, and in some places delivering that warmth upward more effectively than before. NOAA says the shoaling of Atlantic water in the eastern Eurasian basin has brought that warm layer from around 150 metres depth in the early 2000s to as shallow as about 70 metres in recent years, coinciding with the seasonal disappearance of the halocline there and with fast sea ice loss. That's exactly the kind of detail that makes scientists uneasy, because a hidden source of heat is always harder to manage than an obvious one. A hot radiator at least announces itself. A warm current below a cold surface waits until the surface begins to fail. There is a very practical reason this matters so much. Sea ice does not merely need cold air to survive. It also needs the ocean below it to behave. If the water under the ice is carrying upward heat, winter has to work harder. Freeze-up slows. Thickness gains become harder to maintain. The whole system loses some of the margin that used to let it recover from bad seasons. NOAA's 2025 report frames this as an ocean heat and sea ice albedo feedback. Weaker stratification allows more Atlantic heat to ventilate upward. Thinner ice then melts faster in summer, exposing darker ocean surface earlier. That darker open water absorbs more solar energy, which adds still more heat to the upper ocean and sets the next season up badly. The Arctic, in other words, is not just warming because there is more heat around. It is warming because several kinds of heat are beginning to cooperate. That is never the sort of teamwork scientists enjoy seeing. The upper ocean has its own hidden heat problem, and this one is easier to picture because it comes from sunlight. NSIDC explains that as sea ice retreats, darker open ocean absorbs more solar energy. raising temperatures and setting off a cycle of warming and further melting. NOAA's 2025 Sea Surface Temperature Assessment says Arctic summer SSTs are strongly influenced by how much solar radiation the ocean absorbs, with greater warming in ice-free regions, and that August sea surface temperatures north of 65 degrees north have warmed by about 0.3 degrees Celsius per decade from 1982 to 2025. In the Atlantic sector, marginal seas, August 2025 temperatures were as much as about 7 degrees Celsius above the 1991 to 2020 August mean, with temperatures reaching about 12 degrees Celsius in parts of the Barents and Kara Seas. That is an extraordinary sentence to associate with the Arctic, even though it comes with regional limits and seasonal context. When parts of the ocean at the edge of the ice are running that warm, the old picture of the far north as a place where cold always dominates starts looking badly outdated. This summer heat does not simply vanish when the sun angle drops. That would be far too convenient. Isinowawa notes that higher summer sea surface temperatures are associated with delayed autumn, freeze-up and increased ocean heat storage throughout the year. NSIDC made the same point in late 2024, noting that autumn freeze-up has been slow in the Arctic because of growing heat in the ocean mixed layer during summer and higher air temperatures. The logic is annoyingly straightforward. Before sea ice can form, the ocean has to release the excess heat it stored during summer. If the water is warmer, that release takes longer. If freeze-up starts later, the ice-growing season shortens. If the season shortens, the ice that does form has less time to thicken. The result is not just a warmer ocean, it is a calendar shift. The Arctic begins autumn with heat still in the bank, and winter arrives to find the account not yet cleared. That point is worth dwelling on because it helps explain why scientists are often more troubled by stored heat than by headline temperatures alone. A warm day is one thing. A warm ocean mixed layer entering autumn is another. The surface can cool quickly. Water does not always oblige so neatly. It holds heat, spreads it, and releases it on its own schedule. In the Arctic, that delay matters because the whole seasonal rhythm is tight. Animals, storms, clouds, mixing and ice growth all key off timing. NSIDC notes that with less autumn sea ice, increased air-sea coupling can also lead to more low-level clouds over open water, and those clouds can further delay autumn sea ice formation. So the hidden heat in the upper ocean does not remain a purely oceanic issue. It spills into the atmosphere, alters surface conditions, and complicates the already delicate transition from open water back to winter ice. The Arctic is often described as a feedback-rich environment. This is what that looks like when translated into ordinary terms. One source of stored warmth rarely travels alone for long. There is also a quieter source of heat arriving from land, which sounds almost unfair once you learn about it. NASA reported that warm river waters draining into the Arctic Ocean contribute to summer sea ice melt, especially in coastal regions. In the Beaufort Sea, satellite observations of the Mackenzie River outflow during 2012 showed a sudden influx of warm river water that rapidly warmed the ocean surface layers and enhanced sea ice melt. NASA quotes the study team saying rivers act as effective conveyors of heat across immense northern hemisphere watersheds. The impacts are growing for 3 reasons NASA highlighted. Discharge volumes have increased, rivers are warming as their watersheds warm, and Arctic sea ice has become thinner and more fragmented, making it more vulnerable to rapid melt. It is an almost rude bit of systems behaviour. Even the rivers are now delivering extra heat north. The Arctic cannot rely on the surrounding continents to mind their own business anymore. And then, below all of that, deeper than the sunlight, deeper than the halocline, deeper than the upper layers scientists worry about most often, there is still more heat from the Earth itself. The Arctic seafloor is not a dead slab. USGS documents heat flow measurements collected at 356 sites in the Western Arctic Ocean, from a drifting ice island between 1963 and 1973. One of the most remarkable fieldwork arrangements ever devised by people who had clearly decided normal offices were overrated. More recent research synthesizing Arctic geothermal observations reports heat flux estimates ranging from around 30 to 117 milliwatts per square metre in different Arctic settings, including around 80 milliwatts per square metre in the Amundsen Basin and 85 to 117 milliwatts per square metre on the continental slope of the Laptov Sea. That may not sound theatrical, and in truth, it is not theatrical. It is steady. It works from below, continuously, in a place where the water above is cold, salty, dense, and capable of responding to long-term bottom heating in ways that are physically subtle but climatically meaningful. Scientists have known for some time that geothermal heating helps maintain and warm the deepest bottom layers of the Arctic Ocean. The recent Deep Arctic warming study available through PMC explains that geothermal heat supplied from the Earth's interior is an important contributor to warming and maintaining the homogeneous bottom layer of the deep Arctic Ocean, and that continuous heating beneath colder, fresher overlying layers can help drive thermobaric instability and double diffusive convection. Those are technical terms, but the underlying picture is simple enough. When you warm very deep salty water from below while colder, fresher water sits above it, the system does not always remain contentedly stacked forever. Heat and salt do not diffuse at the same rate, and the result can be a staircase-like structure in the water column, with distinct convective layers separated by sharp interfaces. The Arctic deep ocean, then, is not only cold, it is structured by a long negotiation between salinity, pressure, and hidden heat from below. But geothermal heating is not the whole story, and that is where the recent science becomes especially unsettling. The same Deep Arctic warming study found that the Eurasian Basin's deep water between 2,000 and 2,600 metres has been warming at about 0.020 degrees Celsius per decade, faster than geothermal heating alone can explain. The authors argue that warming in the deep Greenland Basin is reducing its usual cooling influence on the deep Eurasian Basin through Fram Strait, effectively transferring deep Atlantic heat into the Arctic. Meanwhile, the Lomonosov Ridge blocks much of that signal from reaching the Amurasian Basin, which has warmed more slowly, around 0.003 degrees Celsius per decade. That is a remarkable finding because it shows the deep Arctic is not simply sitting over background geothermal warmth. It is also responding to changing exchanges with the North Atlantic at depth. Hidden heat is entering the story from below and from the side at the same time. There is another pathway as well, and it sounds almost designed to make the ocean more complicated than any sane person would order. The deep warming study explains that dense shelf waters formed during sea ice growth can cascade down continental slopes as gravity-driven plumes. During descent, those plumes can entrain warm Atlantic origin intermediate water and deliver some of that heat and salt into the abyssal basins. In plain language, a process associated with freezing can also help move warmth downward into the deep ocean. This is exactly the sort of Arctic behaviour that frustrates easy explanations. Nothing stays neatly in one box. Ice formation can produce dense water can sink. Sinking plumes can drag along warmth from another layer. Warmth can then help alter the very deep structure of a basin that, from the outside, most people would classify simply as very cold. The Arctic has a talent for turning simple labels into administrative errors, and then there are the places where the seafloor advertises its heat more openly. NOAA Ocean. Exploration's HACON expedition focused on a hydrothermal vent field about 4,000 metres deep in the ice-covered Arctic, using a vehicle capable of operating tens of kilometres beneath sea ice. Oceanography's account of the Aurora vent field on the Gackel Ridge says evidence of hydrothermal venting there has existed since 2001, with the first visual evidence of black smokers obtained in 2014, and that 2021 brought the first remotely operated vehicle dives to hydrothermal vents under permanent ice cover in the Arctic. These vents are not the main reason Arctic sea ice is declining. Nobody serious is saying the top of the world is melting because a few vents turn the thermostat up downstairs. but they matter for another reason. They prove, in the most direct possible way, that even beneath the deepest, coldest, most ice-covered parts of the Arctic Ocean, the Earth below is still geologically active and still releasing heat and chemicals into the water column. The cold above does not cancel the heat below, it merely hides it better. That matters emotionally as much as scientifically. People are comfortable with the idea of the Arctic as a freezer. Freezers, after all, are supposed to be simple. Put cold things in, close door, truss system, regret forgotten leftovers later. The Arctic is not like that. It is more like a building where the roof is leaking, the basement pipes run hot, the walls are shifting, the thermostat is broken, and the corridors connect to several neighbouring buildings you had not realised were on the same foundation. Warm Atlantic water arrives at depth. Summer, open water absorbs sunlight. Rivers bring heat from vast continental watersheds. The upper ocean stores warmth and delays freeze up. The seafloor contributes background geothermal heat, and in some places hydrothermal systems make that heat dramatic. All of this is happening in a region where sea ice is thinner, younger, and less resilient than it used to be, which means the system has less tolerance for surprises. That is why scientists are so careful when they talk about hidden heat. They do not mean one simple reservoir waiting under the ice like a tank in a basement. They mean a layered set of processes that move warmth into the Arctic and through it in different ways, on different timescales, and at different depths. Some heat comes with currents from lower latitudes. Some comes from sunlight absorbed by newly open water. Some rides north in river discharge. Some rises from the Earth itself. Some is trapped for a season. Some for years. Some deeper still. The real terror, if that word is going to be used honestly, is not that the Arctic contains heat. Oceans always contain heat. The terror is that this particular ocean is losing some of the old structures that used to keep that heat in its place. And once a cold system starts losing control over where its warmth goes, the next change is rarely confined to the water alone. So beneath all that cold, there is warmth moving in from the Atlantic, warmth building in the upper ocean through dark open water, warmth carried in by rivers, warmth rising from the seafloor, and warmth shifting across basin boundaries in ways scientists are still trying to quantify. The ice above may still look white and definite in a satellite image, but underneath it the Arctic has become a place of hidden budgets and difficult transfers, of stored summer heat and upward flux, of weakened barriers and quiet delivery systems. That is the kind of place that does not stay sealed forever. And once a frozen ocean starts opening under pressure from that much warmth, the next part of the story is not hard to guess, even before the ships, routes, noise, and new risks begin to crowd in. And once that hidden heat begins doing its work, the word people reach for is usually open. The Arctic is opening, the sea route is opening, the north is opening. It sounds at first glance like a practical word, almost cheerful. A door opens, a road opens, a store opens, and somebody puts on a sign and perhaps offers you a pastry that was not worth leaving the house for, but at least the mood is optimistic. In the Arctic, though, open does not mean safer, simpler, or settled. It means the protective cover is thinning, the season of exposure is lengthening, and a region that used to resist traffic more effectively is beginning to admit it. Scientists hear that word and think less about opportunity than about consequences. And once that hidden heat begins doing its work, the word people reach for is usually open. The Arctic is opening, the sea route is opening, the north is opening. It sounds at first glance like a practical word, almost cheerful. A door opens, a road opens, a store opens, and somebody puts on a sign and perhaps offers you a pastry that was not worth leaving the house for, but at least the mood is optimistic. In the Arctic, though, open does not mean safer, simpler, or settled. It means the protective cover is thinning, the season of exposure is lengthening, and a region that used to resist traffic more effectively is beginning to admit it. Scientists hear that word and think less about opportunity than about consequences. That is the first thing that happens when the Arctic starts to open. It stops being imagined as a barrier and starts being imagined as a route. The shift sounds small in language, but in practice it changes how governments, industries, researchers, tourism companies, and military planners all look at the same map. A white region people once treated as a limit begins to be discussed as a corridor. And corridors attract attention. They attract cargo models, investment plans, infrastructure proposals, port expansions, search and rescue assessments, insurance arguments, fishing pressure, fuel questions, and the universal human tendency to assume that if a place is sometimes more reachable, it must therefore be ready. Scientists tend to object to that last part. Reachable is not the same as ready. The shipping numbers show how quickly that attention is already becoming traffic. The Arctic Council's Protection of the Arctic Marine Environment Working Group reported in February 2026 that 1,812 unique ships entered the Arctic Polar Code area during 2025, a record high and a 40% increase compared with 2013 when tracking began. Over the same period, the total distance sailed in the Arctic Polar Code area rose 95%, from 6.1 million to 11.9 million nautical miles. The seasonal concentration is just as revealing. In September 2025 alone, 1,060 ships entered the Polar Code area, accounting for 58% of the year's traffic. That tells you something important. The Arctic is not becoming a normal ocean with normal seasons and ordinary marine habits. It is becoming a place where a narrowing annual window is now crowded with more users trying to take advantage of lower ice extent at the same time. The shipping numbers show how quickly that attention is already becoming traffic. The Arctic Council's Protection of the Arctic Marine Environment Working Group reported in February 2026 that 1,812 unique ships entered the Arctic Polar Code area during 2025, a record high and a 40% increase compared with 2013 when tracking began. Over the same period, the total distance sailed in the Arctic Polar Code area rose 95%, from 6.1 million to 11.9 million nautical miles. The seasonal concentration is just as revealing. In September 2025 alone, 1,060 ships entered the Polar Code area, accounting for 58% of the year's traffic. That tells you something important. The Arctic is not becoming a normal ocean, with normal seasons and ordinary marine habits. It is becoming a place where a narrowing annual window is now crowded with more users trying to take advantage of lower ice extent at the same time, and the ships themselves tell their own story. According to the same Arctic Council update, fishing vessels were the most common ship type in the Arctic in 2025, representing 40% of all ships that entered the Polar Code area. General cargo ships were next. Crude oil tankers showed the largest increase since 2013, up 396%, while bulk carriers increased 156%, and cruise ships increased 123%. That is what opening looks like in practice. Not a single heroic vessel cutting through a pristine frontier, but a growing mix of extraction, transport, tourism, and fishing activity pressing into a region that remains seasonally harsh and operationally difficult. Once a place opens in that way, it does not stay a scientific subject only. It becomes an economic one, a regulatory one, and a political one too. The danger is that the language of access can make the place sound tamer than it is. The International Maritime Organization's Polar Code exists precisely because polar waters are inhospitable enough to require mandatory rules on ship design, equipment, operations, training, search and rescue, and environmental protection. That is not the sort of code you write for a region that has become casually manageable. It is the sort of code you write because the cold, the ice, the remoteness, and the consequences of failure remain severe, even when there is more open water than there used to be. the Arctic does not become ordinary, because the navigation season stretches. It simply becomes busy while still retaining most of its ability to punish mistakes. That is one of the most important things scientists and experienced polar operators keep trying to say. Open water is not the same thing as safety. In some respects, less ice can create new hazards instead of removing them. Younger, thinner, more mobile ice can still drift into roots. Storm exposure can increase when open water allows larger waves to build. Weather remains difficult. Distances remain vast. Infrastructure remains sparse compared with lower latitudes. In a place where communications, medical evacuation, towing capacity, and spill response are all harder than they would be farther south, the margin for error stays uncomfortably small. The region may be more accessible than it was, but it is not forgiving. This is why the opening of the Arctic does not only mean more movement, it also means more noise. The Arctic Council's 2025 Underwater Noise Assessment says shipping noise is recognised as a serious environmental problem in the Arctic, with impacts on species, ecosystems and ecosystem services. The report also notes that underwater noise from ships in the world's oceans has roughly doubled every decade since the 1960s and is expected to continue rising. That is especially troubling in the Arctic, because the animals there often depend on sound far more than surface visibility. As more ships move through routes that were once quieter, they do not just occupy the water, they alter the way the water is heard. And because Arctic shipping growth is strongly seasonal, the noise often arrives in concentrated bursts at the very time the ice is at its weakest, and marine access is greatest. That bunching matters. It means ships, animals, and vulnerable habitats are increasingly overlapping in late summer and early autumn, when sea ice is at or near its annual low. A route that opens for business tends to open for many users at once. The result is not simply more sound, but more layered sound. Engines, hulls, propellers, support vessels, fishing operations, cruise traffic, cargo movements, all entering waters where whales, seals, and other species have evolved in a much less crowded acoustic setting. Scientists worry about this because sound is not an optional sense in the Arctic. It is part of how the place functions for the animals living there. Then there is the spill problem, which becomes more serious the moment a route begins carrying more vessels, more fuel, more cargo, and more passengers. Arctic states already have a cooperative framework for this. The 2013 Agreement on Cooperation on Marine Oil Pollution Preparedness and Response in the Arctic was created to strengthen coordination, mutual assistance, training, and information exchange for oil spill response, and Arctic states continue to conduct exercises under that framework. In 2024, for example, the agreement's notification exercise used a scenario involving an expedition cruise ship colliding with a coastal tanker outside Tromsø, with states testing notification and offers of assistance. That is all prudent. It is also quietly revealing. People do not run multinational oil spill exercises in remote cold water because everything is simple and under control. They do it because opening a difficult ocean to more traffic means preparing for accidents that are still hard to manage once they happen. The same applies to search and rescue. The Arctic Council's 2011 Search and Rescue Agreement was explicitly created to strengthen aeronautical and maritime search and rescue cooperation and coordination in the Arctic. That agreement exists because the region's growing accessibility carries obvious rescue implications. As more ships, aircraft, researchers, fishers, tourists, and industrial operators move north, the burden of being able to find and assist them grows too. The practical difficulty is that rescue in the Arctic is not like rescue in a busy temperate sea, with dense infrastructure and short response times. It may involve severe weather, long distances, limited nearby assets, cold water survival issues, and operational windows that close fast. So when the Arctic opens, it does not merely invite traffic, it increases the number of ways something can go wrong far from help. Opening also changes what kinds of environmental stress arrive. The IMO's Arctic heavy fuel oil rules now prohibit the use and carriage of heavy fuel oil in Arctic waters, but the same IMO page notes that certain ships are exempted and that some vessels meeting specific construction standards or operating under temporary waivers may continue until July 1st, 2029. That is not a sign of indifference. It is a sign of complexity. Regulators know the risks are serious enough to act, yet the implementation still has exceptions because shipping systems are rarely simple to change quickly. The point for scientists is straightforward. Once the Arctic opens to more marine traffic, even the fuel question becomes a moving target, tied to spill risk, emissions, operating standards, and the difficulty of enforcing protection in a region that remains logistically demanding. There is another sense in which the Arctic opens, and this one matters even more to biologists than to ship operators. It opens ecologically. NOAA's 2025 Arctic report card says the Arctic is warming several times faster than Earth as a whole, and that this warming is reshaping landscapes, ecosystems, and the livelihoods of Arctic peoples. The report also describes warming waters and borealization, meaning the northward expansion of southern species into Arctic ecosystems. In the northern Bering and Chukchi seas, Arctic species have declined by roughly 2/3 and 1/2, respectively, as boreal species increase over time. That is not just a climate trend. It is a biological border becoming more porous. The Arctic opens, and species from farther south begin entering a system that was once colder, more ice-influenced, and less available to them. That kind of opening does not produce a cheerful increase in options so much as a reordering of who can live where, who gets crowded out, and which food web relationships still work on schedule. NOAA's 2025 productivity assessment says that primary productivity continued to show positive trends in 8 of 9 Arctic regions studied between 2003 and 2025, with very large increases in some areas. But the same assessment emphasises that this does not automatically strengthen ecosystem health. Trophic mismatches can interfere with the movement of carbon through the food chain, and harmful algal blooms are becoming more prevalent. This is one of the central Arctic lessons. More biological activity is not always good news when the timing, species composition and toxin landscape are shifting at the same time. That matters because coastal communities are not standing outside these changes looking in. They are inside them. NOAA's 2025 executive summary says Arctic warming is reshaping the livelihoods of Arctic peoples, and that harmful algal blooms present health risks to subsistence-based coastal communities. It also points to severe storm impacts in Alaska in 2025, where more than 1,500 residents had to be evacuated from southwestern communities after a powerful storm surge and flooding event, with some villages nearly destroyed. The opening Arctic is therefore not just an economic frontier. It is a risk multiplier for the people already living there, people dealing with changing shorelines, changing travel conditions, changing species distributions, changing food safety, and stronger coastal hazards at the same time. That matters because coastal communities are not standing outside these changes looking in. They are inside them. NOAA's 2025 executive summary says Arctic warming is reshaping the livelihoods of Arctic peoples, and that harmful algal blooms present health risks to subsistence-based coastal communities. It also points to severe storm impacts in Alaska in 2025, where more than 1,500 residents had to be evacuated from southwestern communities after a powerful storm surge and flooding event, with some villages nearly destroyed. The opening Arctic is therefore not just an economic frontier. It is a risk multiplier for the people already living there, people dealing with changing shorelines, changing travel conditions, changing species distributions, changing food safety, and stronger coastal hazards at the same time. There's also a less obvious institutional consequence. The more the Arctic opens, the more important long-term monitoring becomes, because the old assumptions stop working. NOAA's 2025 executive summary stresses that maintaining Arctic observing and data sharing infrastructure is critical, and that some observing systems face vulnerabilities and risks just when the need for information is growing. That makes sense. A region under rapid transition needs more measurement, not less. But opening the Arctic often means increasing demands on the same systems that are trying to understand it. More ships, more communities at risk, more wildlife shifts, more hazards, more questions, and still a region with enormous logistical challenges. The Arctic does not become easy to monitor just because it becomes easier to enter. In some ways, it becomes harder because the rate of change and the number of interacting pressures both rise together. So what happens when the Arctic starts to open is not that the region becomes friendlier. It becomes exposed. It becomes busier. It becomes easier to reach and harder to protect at the same time. The ice retreats and a route appears, but so do new costs, new vulnerabilities, and new kinds of damage that do not always reverse once the season ends. Scientists understand that deeply, which is why their unease often sounds less dramatic than the headlines, but more serious underneath. They know that opening is real. They also know that every year the Arctic becomes more available to the rest of the world. It becomes a little less buffered from the rest of the world's habits. And that is exactly where the deeper anxiety begins to sharpen. Because even after all the measurements, all the traffic counts, all the agreements, all the hydrophones, all the maps and models, the people who know this region best still do not speak about it with comfort. And that is the point where the mood changes completely. Up to a certain point, people can listen to all of this as a story about a difficult region, undergoing rapid change. Sea ice is thinner, water is warmer, shipping is increasing, species are shifting. The map looks different. That is all serious, but it still sounds, to many ears, like the kind of serious problem experts are built to handle. Scientists gather data, engineers improve instruments, governments negotiate rules, researchers update models. The machine of a modern knowledge turns over, perhaps with some grinding noises, but still turns. Yet when you spend enough time listening to Arctic specialists, really listening to the tone rather than only the information, another feeling comes through. It is not panic. It is not theatrical dread. It is something more sober and in some ways harder to dismiss. They sound uneasy because they're tracking a system that is changing fast, tied to the rest of the planet, full of feedbacks, only partly observed and increasingly exposed to human pressure at the exact moment it is becoming less predictable. That is not a comfortable combination. One reason for that unease is simply the speed. Scientists are not dealing with an Arctic that is changing over the course of some distant geological patience, while everyone calmly updates a textbook every few centuries. NOAA's 2025 Arctic report card says the Arctic surface air temperature for October 2024 through September 2025 was the highest on record since at least 1900. It also says the region experienced its warmest autumn, second warmest winter, and third warmest summer since 1900. While Arctic autumn and winter temperatures over the past 20 years have risen more than twice as fast as the corresponding global air temperature increases. In the same report, NOAA says the March 2025 sea ice maximum was the lowest in the 47-year satellite record, and the end of summer ice cover in 2025 was younger, thinner, and 28% less extensive than in 2005. Experts feel uneasy because these are not isolated curiosities. They are signs that the physical background conditions they use to understand the Arctic are moving quickly enough to change the meaning of normal within a career. Another reason is that the Arctic does not usually change in one neat direction at a time. It changes through linked processes. NOAA's 2025 executive summary emphasizes the increasing pace, scale, and consequences of rapid environmental change across the Arctic, and highlights the emergence of new and complex feedbacks and interactions. The same report ties together widespread warming, sea ice loss, permafrost thaw, changing river chemistry, shifting marine productivity, borealization on land and sea, and Atlantification in the ocean. That matters because experts are often most uneasy not when one variable changes, but when several begin moving together and start amplifying one another. A system with one problem can sometimes be contained. A system in which heat transport, sea ice, ecosystem structure, coastal risk, and observation gaps are all interacting is much harder to box in. The Arctic has become that second kind of system. The hidden ocean heat makes this especially troubling. NRA's Atlantification assessment says warmer, saltier Atlantic origin water is now reaching the central Arctic Ocean, that this process weakens Arctic stratification, enhances heat transfer to the surface, and undermines sea ice resilience. The report adds that Atlantification is already advancing toward Alaska and is reshaping ecosystems while threatening climate stability. Researchers know from experience that hidden heat is more dangerous than visible heat because it can sit beneath an apparently cold surface while steadily removing the system's margin for recovery. That is why experts do not sound reassured even in years when the Arctic still freezes over widely in winter. The surface may still appear frozen, but the structure beneath it is less stable than it used to be. There is also the problem of uncertainty, and not the lazy kind where nobody has looked. The Arctic is one of the most studied difficult places on Earth, yet major blind spots remain because the environment itself obstructs observation. NOAA's assessment of the Arctic Observing Network says persistent gaps in observing systems limit our ability to fully understand and respond to changing conditions. It points to sparse precipitation gauges, unreliable infrastructure, and limited telecommunications as obstacles to in situ monitoring. It also notes that satellite systems face Arctic-specific limitations because geostationary coverage degrades above 60 degrees north, cloud cover masks many signals, limited daylight removes others, and resolution is not always adequate. Experts feel uneasy because the Arctic is not just changing rapidly, it is changing in a place where the usual tools of confidence are weaker than they are farther south. That uncertainty extends to the shape of the region itself. The 2024 IBCAO version 5.0 publication reported that only 25.5% of the seabed 2030 Arctic region is constrained by direct depth measurements, even after major improvements in mapping. That is a remarkable figure for an ocean that plays such an important role in global climate, circulation, and sea ice behaviour. Scientists have every reason to be uneasy when a region matters this much, and large parts of the seafloor are still being brought into clear view. The shape of the seabed affects currents, mixing, and the movement of heat. If the floor plan is still incomplete, then some of the behaviour above it remains harder to interpret than anyone would like. Then there is the problem of memory. Experts are trained by old records, old field conditions, old assumptions about how the pack behaves, where multi-year ice tends to persist, what species appear where, when freeze-up usually happens, and which regions are buffered by the old Arctic structure. But NOAA's current sea ice assessment says the thickest, oldest ice has declined by more than 95% since the 1980s, and is now mostly limited to areas north of Greenland and the Canadian archipelago. The same assessment stresses that the profound sea ice changes since 2005 are opening the Arctic to more human activity, while raising concerns about safety, security, and the environment. This means experts are increasingly forced to operate in an Arctic, where their earlier experience remains valuable, but cannot always be treated as a reliable guide to present-day behaviour. That is deeply unsettling for any field scientist. Familiarity becomes less protective when the system itself is losing the features that made it familiar. Ecology adds another layer of discomfort. NOAA's 2025 Executive Summary says that during 2003 to 2025, primary productivity increased in 8 of 9 Arctic regions examined. But it also warns that more productivity does not automatically mean a healthier ecosystem. It highlights trophic mismatches, the northward expansion of southern species, and harmful algal blooms that pose health risks to subsistence-based coastal communities. The same report says Arctic species in the northern Bering and Chukchi seas have declined by roughly 2/3 and 1/2 respectively, as boreal species increase over time. Experts are uneasy because ecological reorganization is harder to reverse than a simple change in seasonal ice extent. Once food webs shift, once toxins enter new parts of the chain, once species ranges move and old timing relationships break, the system is not just warming, it is being rewritten. And this is where the human dimension becomes impossible to ignore. NOAA's 2025 Executive Summary says Arctic warming is reshaping the livelihoods of Arctic peoples, and that the region's transformations will affect the well-being of Arctic residents while influencing the trajectory of the global climate system more broadly. The report also describes record-high annual precipitation in 2024 to 2025, increased extreme precipitation, rapid spring snowmelt, and more than 200 discoloured rusting rivers tied to thawing permafrost and worsening water quality. Those are not abstract geophysical curiosities. They are things that affect travel, drinking water, fisheries, infrastructure, and food systems. Experts feel uneasy because the Arctic is not just a laboratory. People live there. A changing ocean and changing ice regime are connected to roads, homes, coastlines, hunting routes, and the reliability of subsistence foods. Even the systems meant to track these changes are under strain. NOAA's 2025 Observing Network essay says the resilience of the internationally supported Arctic Observing Network depends on sustained investments, protection of specialised expertise, and continuity of both satellite and in-situ observing systems. The executive summary adds that maintaining Arctic observing and data sharing infrastructure is critical, and notes vulnerabilities and risks facing nationally and internationally coordinated observing programs. That is one of the more quietly alarming parts of the whole picture. The Arctic is changing fast enough to require long, uninterrupted records and broad cooperation, yet the systems that deliver those records are not invulnerable. Experts are uneasy in part because they know how much of modern understanding depends on continuity, and how damaging it can be when continuity breaks in the middle of a transition. There is also a plain operational reason for the unease. As the ice retreats, more people, vessels, industries and governments are moving into the region. The Arctic Council reported in February 2026 that 1,812 unique ships entered the Arctic Polar Code area during 2025, a 40% increase from 2013, while total distance sailed rose 95% over the same period. September 2025 alone accounted for 58% of annual traffic. NOAA's sea ice report links declining ice directly to greater human activity and rising concerns about safety and security. Experts know what this means in practical terms. Every new vessel, every additional tourist route, every fishing expansion, every cargo movement, and every industrial plan adds more chances for spills, noise, collisions, rescue failures, ecological disturbance, and policy conflict in one of the least forgiving marine environments on Earth. It is hard enough to track a rapidly changing Arctic. It is harder when the changing Arctic is also getting busier. That traffic brings sound with it, and sound matters more in the Arctic than many outsiders realise. The Arctic Council's 2025 Underwater Noise Report says underwater noise from shipping is recognised as a serious environmental problem in the Arctic, with impacts on species, ecosystems, and ecosystem services. The report models large increases in underwater noise across the Arctic Ocean by 2030 as shipping grows and sea ice conditions change. Experts are uneasy because marine mammals in the Arctic rely heavily on hearing to navigate, feed, and communicate. In a place where sound is a primary way of sensing the environment, noise is not an inconvenience. It is interference with the basic operation of life. A busier Arctic is therefore not simply a more industrial Arctic. It is a less legible Arctic for the animals living in it. There is a strategic dimension too, though scientists often speak about it more carefully than politicians do. NOAA's 2025 sea ice report says reduced sea ice is driving a re-evaluation of resource extraction and national security activities in the Arctic. That sentence is doing a great deal of work. It means the region is no longer only a climate problem, an ecosystem problem, or a logistics problem. It is also becoming a theatre of infrastructure planning, maritime control, economic competition, and security policy. Experts feel uneasy because scientific uncertainty becomes harder to manage when it sits next to geopolitical urgency. The faster a region gains strategic attention, the harder it becomes to keep long-term stewardship at the centre of decisions. What makes all of this worse is that the Arctic tends to hide thresholds until they are close. NOAA's reports do not generally speak in the language of melodrama. They speak about weakening stratification, diminished winter sea ice formation, increased productivity, changing species composition, and the emergence of new and complex feedbacks. But for experts, that phrasing carries its own warning. Systems with feedbacks can look manageable for a while, and then shift more abruptly than the public expects. A halocline can weaken, seasonal timing can slide, a species' range can move north quietly for years, and then suddenly feel transformed to everyone who depends on it. Unease lives in that gap between gradual data and sudden consequences. Scientists do not necessarily fear one spectacular Arctic collapse scene. They fear accumulated change arriving in enough places at once that adaptation starts lagging behind reality. There is also the uncomfortable truth that the Arctic now tells experts something about the rest of the world. NOAA's executive summary says the Arctic's roles in global climate, economic and societal systems are transforming, and that observing the Arctic is effectively taking the pulse of the planet. That is not rhetorical flourish. The Arctic is tied to heat transport, sea level through Greenland ice loss, weather patterns, fisheries, shipping, and global climate feedbacks. Experts are uneasy because what they see in the Arctic is not only a regional story. It is often an early and amplified version of larger planetary change. A place once treated as remote has become diagnostic. When the far north starts behaving differently, it is rarely only the far north that matters, and perhaps that is the deepest reason they still sound uneasy even after decades of work. It is not because they know too little. It is because they know enough to see the structure of the problem. They know the Arctic is warming exceptionally fast. They know the sea ice cover is younger and thinner. They know warm Atlantic origin water is pushing farther in and weakening the old insulation from below. They know ecosystems are shifting, ship traffic is climbing, and observing networks still have serious gaps. They know parts of the seafloor remain incompletely mapped, while the living systems above them are already responding to new conditions. They know communities are being affected now, not in some remote future, and they know that in systems this connected, faster than expected, does not have to appear everywhere at once to become dangerous. So even the experts, the people with the moorings, the satellite records, the ice cores, the hydrophones, the climate models, the field seasons, and the very disciplined habit of understating things in public still feel uneasy here because the Arctic is no longer merely severe. It is unstable in ways that matter, exposed in ways that invite pressure, and only partly visible at the exact moment when the consequences of misunderstanding it are growing. That is why their language keeps returning to continuity, resilience, gaps, risk, and the need to keep watching. They are not waiting for one final disaster to make the place serious. The seriousness is already here, and once you understand that, the last movement of the story becomes quieter rather than louder, because what remains most haunting about the Arctic is not a single event. It is the silence that returns after all the data, all the alarms, all the ships, and all the warnings, as if the frozen world is still there, still watching, and still not finished telling us what it will do next. And perhaps that is why the ending never really feels like an ending when the subject is the Arctic. Most places, once explained, begin to settle in the mind. They become clearer, their boundaries sharpen, their risks sound measurable. You may not like the answer, but at least the answer arrives and takes a seat. The Arctic does not do that very often. Even after the data, the expeditions, the maps, the cores, the hydrophones, the models, and the years of patient work, it still leaves people with the same uneasy feeling they had at the start, Only now the feeling has reasons attached to it. At first, many people imagine fear as a problem of not knowing enough. You're afraid because the room is dark, because the road is unfamiliar, because the sound in the wall has not yet been identified as either old pipes or a raccoon with terrible timing. But the Arctic creates a different kind of fear. Here, experts do know a great deal. They know the region is warming far faster than the planet as a whole. They know the sea ice has become younger, thinner, and less extensive. They know the Arctic's roles in climate, ecosystems, economies, and human livelihoods are changing at the same time. NOAA's 2025 Arctic report card is very clear on that point, describing the Arctic as warming several times faster than Earth overall, and calling it a place whose transformations matter well beyond the North itself. That is why the silence feels different now. It is no longer the silence of a place people once assumed was empty. It is the silence that remains after a warning has been understood. The scientists are not uneasy because they think the Arctic is a mystery in the old romantic sense. Some blank white corner waiting to be filled in by brave people with flags and poor handwriting. They're uneasy because the region is changing in ways that are visible enough to confirm, fast enough to matter, and complicated enough that no honest person can pretend the whole picture is neatly under control. One of the hardest facts to sit with is how normal this has all started to sound. Record warmth, record low winter sea ice, more shipping, more open water, longer melt seasons, more ecological rearrangement. These phrases arrive so often now that the ear begins to adapt to them, which is one of the more dangerous habits human beings have. We are very good at turning repeated warnings into background furniture, yet the underlying numbers are still startling. NSIDC reported that the Arctic sea ice maximum on March 22, 2025, was the lowest winter maximum in the 47-year satellite record, and that the September 2025 minimum still ranked among the 10 lowest on record, with the last 19 years containing the 19 lowest September extents in that record. Those are not small fluctuations around a stable norm. They are the signs of a system that has already moved far from the older conditions many experts were trained to expect, and still even that does not quite explain the emotional weight of it. Numbers matter, but numbers alone do not produce that specific Arctic unease. The unease comes from the way everything in the region now seems to carry two meanings at once. Open water means access, but it also means absorbed heat. Thinner ice means easier passage, but it also means less protection and less recovery time. More biological productivity may sound encouraging until you notice the timing shifts, the toxins, the species moving north, and the food web links coming under pressure. More traffic can be called development in one meeting and disturbance in another. Every gain has a cost attached to it somewhere else. Every change opens one door and closes another. That is one reason the Arctic feels so difficult to talk about honestly. People tend to prefer a cleaner story. Either the North is a tragic victim, or it is a new frontier. Either it is empty and vulnerable, or it is useful and available. Either the science is settled enough to justify confidence, or uncertainty gives everyone permission to keep acting, as though the future is still a matter of preference. The real Arctic refuses all of that. It is a changing ocean system under strain, biologically rich, physically harsh, culturally inhabited, economically tempting, and globally important all at once. It is very hard to fit that into a slogan, which is unfortunate because slogans are exactly what public discussion tends to demand. Meanwhile, the region goes on changing without waiting for the language to improve. Even the word watching starts to make practical sense after a while. Not in a supernatural way, not as though the Arctic has intentions hidden under the ice. The watching comes from the records it keeps and the signals it sends. The ice records old air, the seafloor records former ice positions and older climates. The ocean records heat transport in its layers. The animals record shifts in prey, toxins, and movement. The soundscape records cracking ice, moving mammals and growing traffic. The satellites record the surface, The moorings record what the surface cannot show. Everywhere scientists turn, the Arctic is leaving evidence. The silence watches back because it is not truly silent. It is full of measurements waiting to be interpreted correctly. And those measurements have become harder to dismiss. The Arctic Council reported in early 2026 that 1,812 unique ships entered the Arctic Polar Code area during 2025, a 40% increase since 2013, while total distance sailed in the area increased 95% over that same period. That matters not just because it shows more activity, but because it marks a deeper change in the way the Arctic is being treated. A place that once functioned as a barrier is now being used more and more like a route. That shift is not theoretical anymore. It is already visible in the traffic, and once a region becomes a route, the rest of the world arrives with all its usual habits: engines, schedules, fuel, insurance, extraction, tourism, noise, deadlines, political tension, safety codes, economic arguments dressed up as inevitabilities. A route is never only a line on water. It is a claim about use. Scientists know this, which is why many of them sound most uneasy, not when they describe the climate data, but when they describe the combination of climate change and exposure. The Arctic is becoming easier to enter while still being extremely difficult to protect. That is an especially bad combination for a place where mistakes are expensive and recovery is slow. At the same time, the old cover is not simply vanishing and leaving behind a simpler world. The region is becoming more active in ways that complicate every layer of the story. The water beneath the ice is carrying heat. The upper ocean is storing more solar energy where open water appears earlier. The biological timing that once worked under stronger seasonal patterns now has to operate in a less reliable schedule. Monitoring systems still have gaps. The seabed is not fully mapped. Species are shifting. Harmful algal blooms are becoming more relevant in places where they matter directly to subsistence foods and coastal communities. The Arctic is not only losing ice, it is gaining in stability. That is a less dramatic sentence than many headlines prefer, but it is probably closer to the truth than most dramatic sentences are. Because instability is what experts are trained to respect. A harsh system can still be workable if its behaviour is familiar. A dangerous region can still be studied if the patterns hold long enough. Even a remote ocean can be managed, at least in parts, if the structure of the problem stays recognisable. But when the pace of change increases, when multiple feedbacks begin interacting, when the old physical protections weaken, when traffic rises, and when the observing system itself has vulnerabilities, the work becomes less about understanding a known machine and more about tracking a machine that is being rebuilt while it runs. That is why the tone of Arctic science so often sounds careful rather than loud. Careful is what people sound like when they know enough to avoid simple comfort. Careful is what happens when researchers are watching a place whose past records show large shifts are possible, whose present measurements show active change underway, and whose future matters to far more than the small number of people who will ever stand on the sea ice themselves. It is not fear in the childish sense, it is disciplined concern. And in some ways, disciplined concern is more persuasive than drama, because it usually means the people speaking have already passed through drama and decided the facts were serious enough on their own. There is another reason the ending feels quiet. The Arctic does not usually announce itself with a single final event. It changes in accumulated ways. More rain where there used to be more snow, more heat stored in summer water, less older ice surviving through the melt season, more vessels in September. More signs that species from farther south are moving into places once too cold for them. More evidence that the ocean's hidden structure is shifting below the surface. NOAA's 2025 reporting presents exactly that kind of picture. Not one spectacular collapse, but a growing pattern of linked changes across sea ice, oceans, ecosystems, and human communities. The human mind often struggles with problems that arrive this way. We are much more comfortable with things that happen once loudly and in a format suitable for moral clarity. A storm destroys a harbour, a bridge collapses, a mountain erupts. Those events are terrible, but they are simple to recognise. The Arctic is harder because much of its danger lies in the slow loss of older protections and the steady rise of new pressures. It is not one door slamming. It is a house becoming less sound in 20 different places at once. And perhaps the most unsettling detail of all is that the Arctic is not far away in the way people once thought. On a map, yes. In ordinary daily life, certainly. But physically and politically, no. What happens there does not remain there. The Arctic helps regulate heat, light reflection, ocean processes, ecosystems and weather-linked systems that connect outward into the rest of the world. NOAA's 2025 summary makes that point directly, describing the Arctic as tied to global climate, economic and societal systems, and saying that to observe it is to take the pulse of the planet. Experts feel uneasy because they are not looking at a remote curiosity. They are looking at a sensitive part of the operating system. So when the silence returns at the end of all this, it is not the old silence of ignorance. It is the silence after a diagnosis. You can still stand under a dark sky and think the far north looks blank from a distance. You can still see photographs where the ice appears smooth enough to calm the mind. You can still imagine, for a moment, that a frozen place must be a stable one. But once you know what is under the surface, the idea does not hold. You know there is heat moving in layers below the cold. You know the ice cover is thinner and younger than it once was. You know the ocean beneath is busy, the animals beneath are listening, the seafloor beneath is keeping records, and the roots above are attracting more and more human attention. That is why the Arctic stays with people. It is not merely cold, it is not merely remote, it is not merely changing. It is a place where hidden movement matters, where appearances mislead, and where the consequences of being wrong are spread across years rather than moments. The scientists who work there understand that in their bones. They come back with measurements, but also with tone, and the tone says something very plain. This is not a system anyone should speak about casually anymore. Maybe that is the most honest way to end it. Not with a dramatic warning, not with a final flourish about doom, just with the recognition that the frozen ocean beneath the Arctic still frightens careful people for very practical reasons. It is active where it looks still. It is connected where it looks remote. It is vulnerable where it looks hard. And it is changing while more of the world pushes in. So tonight, wherever you are listening from, in a warm room or a quiet room, or a room with some faint sound from outside that reminds you the world is still moving, try to hold the real image of the Arctic in your mind for a moment. Not the postcard version. Not a white patch at the top of a classroom globe. Think instead of an ocean under ice that drifts and breaks. Think of dark water holding heat below colder layers. Think of whales navigating by sound in water that is growing busier. Think of ancient air trapped in ice. Think of seabeds keeping long records under a cover that no longer protects quite the way it used to. Think of researchers reading all of that and still choosing their words carefully. Because careful words, in places like this, are often the clearest sign of all. And now, as the lights lower on this subject and the mind begins to loosen its grip a little, perhaps the most fitting thing is not to force one last conclusion onto it. The Arctic has never been a place improved by haste. Better to leave it as it is. A cold ocean with too much history in it. A changing ocean with too much at stake. A region that can still look empty from far away even after you know it is full of motion, memory and warning. That may be why its silence lingers. Not because it says nothing, but because it says enough, then waits. And if you listen closely, it still sounds like a place that is not done.